Hey, and how's life in your household?
Life's pretty good. My son has been obsessed with Pokemon, but now he won't talk about electric type Pokemons like Pikachu because it just leads me to explain something else about electricity that he doesn't want to hear.
My daughter's also like, okay, when are you going to read something else other than The Grid? There's a lot of books called The Grid. They're all great. So there's a machine that beats precisely 60 times a second. Its arteries stretch from powerful waterfalls to massive fuel burning plants, where huge turbines spin together in perfect harmony to generate the entire system's 60 hertz heartbeat.
These arteries meet a dense web of capillaries, smaller lines that distribute power to light up the bulbs above your head, charge the phone at your bedside, and power the gears of factories and chips at data centers.
You flip a light switch in your kitchen and the whole system feels it. A turbine 1,000 miles away feels the drag of your light bulbs physically pulling on them for power. The grid truly acts as one big machine.
In the US, we built this miraculous system not through some grand design, but through a century and a half of decisions with unforeseen consequences. From merging mini grids together to pooling power to fight wars to creating a patchwork of institutions, all to deliver power to every outlet every second. And for most of the journey, it's been an economic miracle.
That's right, electricity kept getting cheaper, decade after decade after decade for nearly a century. And it didn't start that way. It started as the ultimate luxury, upgrading the lighting at JP Morgan's house. It then became so universal and so cheap that we stopped thinking about it almost entirely. The grid became physically and economically invisible to the average person.
But that invisibility, while a sign of progress, has also become a source of vulnerability. Because right now, the system is in crisis. It's on the front lines of a changing climate, both in cause and effect.
And for the first time in decades, we're asking the grid to grow significantly to power the electrification of transport, of industry, and of course, data centers. And that promise we made of economic invisibility is now shattering, as nearly a third of Americans struggle to pay their electricity bills.
The story of the grid is an epic. It's a story of inventors and electrocutions, of a man who brought power to the masses and then lost everything, of an America that built massive new industries to win wars.
It's a story of regulatory complexity and market failures, of massive power outages and catastrophes, of a bet on the future of artificial intelligence and abundant energy sources.
Of a $1 trillion energy transition that we are living through right now. This is the story of an aging machine of immense and increasing importance.
Welcome to the story of the grid. Well, hello, listeners. Welcome to the 2026 season of the Step Change Show. We're here to cover the stories of human progress. We want to understand the technology, systems, and infrastructure that shape our world. And I'm Ben Idelson. I'm a co-founder of Step Change Ventures, a fund that invests in the companies that are accelerating today's biggest step changes. And I'm based up in Seattle, Washington.
And I'm Anai Shah, fellow co-founder of Step Change Ventures and based in Los Angeles, California. Now, before we dig into the epic of the grid, we have just one quick note. We have all the research links and notes for this episode up on stepchange.show.
And if you're listening to this and think of a friend or colleague who might enjoy it, please send it their way. This is still a very new show, and we appreciate it finding the right listeners.
And we want to give a big thank you to Crusoe, our presenting sponsor for this episode.
Crusoe is very relevant to the evolving story of how the grid intersects with data centers, as we'll share more about in a bit.
So let's begin this story in ancient Greece.
Someone's rubbing a piece of amber against a cloth, and suddenly it's pulling feathers toward it like magic. There are no wires, no batteries, just this stone with some invisible power. The Greeks called what we now call amber, they called it electron, which now gives us the word electricity.
And so it wasn't until the 1700s that we made that next leap of progress after the ancient Greeks. England needed better compasses to rule the seas, which meant understanding magnetism. So by the mid-1700s, scientists had built machines that could generate this electrical effluvia more reliably than just rubbing amber.
So at this time, electricity was used much more for a kind of showmanship demonstration. These were spectacles. They were creating sparks, making people's hair stand on end. Crowds would come for the entertainment purpose.
And one of those showmen hosting electricity demonstrations was a fairly famous figure in American history, right?
That's right. In 1746, you had Benjamin Franklin, a famous printer, businessman, and just a relentlessly curious mind. And he got his hands on a Leyden jar. It's like an early capacitor that could store and discharge electricity as sparks. And he became obsessed. He started filling his Philadelphia home with crowds that were eager to witness what looked like magic.
And this obsession meant that he didn't want to just perform, he wanted to understand it. And so he gave us the terms positive and negative charge. He wired up multiple jars together and called the array an electrical battery. Then came the kite, the famous kite experiment. In 1752, he flew one into a storm cloud, not to get struck by lightning, but to prove lightning was electricity. And it worked. Within months, his lightning rod was appearing on buildings across Philadelphia, Boston, London, Paris. The first time in human history we could defend ourselves against this shock from the sky.
And so Franklin's triumph raised, of course, a bunch of new questions about the nature of electricity. If lightning was electrical, what exactly was electricity? Where did it come from? Was it a fluid? Was it a force? Was it something else new entirely?
And these questions that you mentioned, Ben, would spark the next great electrical controversy. And it turned into a battle between actually two Italian professors who started with dead frogs and ended with an invention that could potentially change the world.
So Professor Galvani was dissecting frogs, and he realized that the frog's legs would twitch whenever there was an electrical storm outside, and he thought he had figured out the secret of life. It was animal electricity. And this became a big sensation across Europe. But a different professor, Alessandro Volta, disagreed with this entirely. He thought that the electricity was not coming from the frog, but coming from the metal that was touching the frog. And so he set out to devise a scheme to disprove this.
And so we're in 1794. Volta goes public with this challenge. It's animal electricity versus metallic electricity, or the Galvanists versus the Voltaists. And so to prove his point, Volta needed to create electricity without any frog tissue. And so he started very simply. Zinc and copper discs, separated by cardboard, soaked in salt water. Stack them up, connect them top to bottom with a wire, and something remarkable happened. The wire started to warm, and the flow didn't stop. It kept going as long as the metals were connected. Volta had just created the world's first battery, unveiled in 1800. No dead frogs.
And so the static electricity that Franklin was playing with gave you a spark, but Volta's battery gave you a river, a current of electricity that you could channel, study, and then use. And with batteries in hand, a new generation of scientists was about to discover what you could actually do with electricity.
So in 1809, a Humphrey Davy put on what one witness would call the most dazzling lecture. He connected a powerful battery to two carbon rods, brought them close together, and created something extraordinary. An arc of electricity jumped between them, and this produced a light so bright for the people in the audience, they had to shield their eyes. And this was the arc light. For the first time, electricity went from a curiosity to actually something useful.
And so from here, scientists across Europe built bigger and more powerful batteries, and with them came a cascade of discoveries. Most intriguingly, the realization that electricity and magnetism seem to be intimately connected. You had scientists like Ampere, where we get the unit of current for amps, that realized that the strength of the magnetic field intensified with the rise of the power of the electric current. This was then built upon to create really powerful electromagnets.
You wrap wire around an iron core, you run current through it, and you could lift thousands of pounds. And then you turn off the current, and the magnetism vanished instantly. They had just created magnetism on a switch. But these batteries had a fundamental flaw. They were just converting. They weren't generating, right? They turned the chemical energy into electrical energy, consuming the materials in the process. But every battery eventually ran down, the metals corroded, and its solutions were exhausted.
The real prize would be if they could find a way to generate electricity mechanically, to convert the motion into current. If electricity and magnetism were so connected and magnets could create motion, couldn't that motion somehow create electricity? And now it's time to introduce a scientific hero, Michael Faraday.
Michael Faraday started his life about as far away from science as you could get. His father was a blacksmith, and young Michael apprenticed as a bookbinder. This is a great turn of events where he's binding books, but instead of just binding scientific texts, he read them, devoured them. He taught himself chemistry, physics, mathematics, and he went and attended a public lecture by one and only Humphrey Davy, who we talked about. And Faraday took meticulous notes, and then he bound his notes, being a bookbinder, into a beautiful presentation that impressed Davy so much that Davy hired him as an assistant.
And Faraday became obsessed with this connection between electricity and magnetism. If electric current could create a magnetic force, surely the reverse must be possible, that you could use magnets to create electricity. And in 1831, the breakthrough happened. He moved a magnet through a coil of wire and detected an electric current, realized that motion with magnetism would equal electricity.
This seems too simple to be true. An electric current is set up in a closed circuit by changing the magnetic field. So, as long as you keep something moving, a wheel turned by water, a crank turned by hand, anything, you could generate electricity continuously. We just discovered that mechanical energy can be transformed directly into electrical energy.
Faraday had just invented the fundamental principle behind every power plant that would then come. Fast forward nearly 40 years after this, and humanity now had the ability to generate electricity with dynamos. We had the ability to store it in batteries. We could capture lightning in a jar. We understood the mathematical laws governing what was going on, but we still didn't really quite have a practical use for all of this discovery.
Yeah, we had just spent a century unlocking electricity's secrets: produce it, control it, measure it, store it. But we had almost nothing to do with it. It was kind of like having fire, but nothing to cook, or a wheel, but nothing to roll. And many suspected that the answer would involve light.
So during the period we're about to enter, the turn of the century, we see a fundamental reshaping and reshuffling of so many elements of society. We're about to have the explosion of steel from the Bessemer process, the connecting of the country from the railroads, and the real beginning of mass urbanization. In fact, many people call this period the second industrial revolution. But inside people's homes, there's a more foundational desire, a desire for better and cleaner light. But before we tell the story of how light was about to become electricity's killer app, it's a great time in our story to thank our presenting sponsor, Crusoe.
Yes. And as we entered the late 1800s, we had so much going on reshaping society. And as we'll see in a moment, a few core companies take center stage at designing the future of electricity. Those that made the most progress were designing the whole system end to end, thinking about how to build everything from the first power station to the light bulb in the home. And today, we're in another moment of massive transformation for society, this time with AI at the center. And the companies that are making some of the fastest progress are those taking on the whole problems end to end.
That's right, and Crusoe really is a unique company in this way. They are the vertically integrated AI company. They build everything from getting power to the GPUs to building the inference cloud product that end builders can use. And as we got to know the Crusoe team, we learned something surprising about how deep this vertical integration went.
We learned that they actually began manufacturing all of their own in house power equipment. These are the switchgears, power distribution centers, control panels, switchboards. This is everything you actually need to route power from the substation to the GPUs that are going to train or run your models.
And as we'll talk about later in our story, data centers can be bottlenecked by available power on the grid. But once they have a site permitted and powered, there's a whole supply chain of equipment needed to get that site live. So it makes so much sense that Crusoe would go and solve their own bottleneck here. They built out over 3 gigawatts of AI infrastructure using equipment designed by their team of engineers made in house here in the US, in Colorado, Louisiana, and Oklahoma. And while they built this capability to power their own data centers, they've now decided to make it available to the broader market.
And with this tested equipment built domestically, you can get shorter lead times, reduced tariff exposure, and products made by the leading AI company. Everything is made to UL, ISO, and IEEE specs.
That's right. So if you're planning a data center build out or expansion, we recommend heading over to crusoe.ai/stepchange to understand the products they have and quickly get a quote from the Crusoe Industries team. They'd be happy to help you get your data center built faster. As we think about the most interesting companies at the center of both AI and energy, we can't think of a better partner. Head to the link in our show notes, and thanks again, Crusoe.
Okay, Ben. Well, before we get too passionate about the AI build out, we need to get that dirty coal gas out of our houses. So, what was lighting houses back in the 1870s?
The urban centers of America glowed with coal gaslight. There were over 400 gas companies that piped coal gas through underground networks, lighting streets and homes with this warm, glowing light. And coal gas was a massive industry. In fact, we had talked a lot about this back in our episode about coal part two, but its days were ultimately numbered.
And this revolution, it started ugly, a little bit piecemeal, right? So, you had the blinding light that Davy demonstrated 40 years back. And now we're in 1879, and the California Electric Company had strung these arc lights throughout San Francisco, but they were harsh, blazing lights, and they had to be mounted on towering poles so the glare wouldn't hurt people's eyes. And right around this time, Edison sees arc lights for the first time. He becomes transfixed. The problem was that the light was too intense, too concentrated. But what Edison saw, as he said, the intense light had not been subdivided so that it could be brought into private houses. Edison wasn't just thinking about light bulbs. He was thinking about building a system and an industry to replace coal gas.
Just 1 or 2 months later, in October of 1878, Edison doesn't have a working bulb yet. I don't even know if he has a prototype. It doesn't matter. He goes straight to the press, what a showman, and says, "The same wire that brings you the light will also bring you power and heat. You may cook your food with it." And he's already seen past illumination to an entire electrical civilization. This whole announcement crashes gas stocks both in the US and in the UK. The British Parliament actually appointed a committee to investigate Edison's claims. And they came back saying, his dreams are good enough for our transatlantic friends, but are unworthy to the attention of practical or scientific men. Edison didn't care. He incorporated the Edison Electric Light Company to go make this happen.
And so what Edison needed to do was find the right filament to burn inside the light bulb. And so for a year, his team tested everything: platinum, bamboo, human beard hair. And finally, in 1879, a carbonized cotton thread burned for 14 and a half hours. And on New Year's Eve, 3,000 people descend to see Edison's electric lights. And what Edison understood was that he wasn't just going to replace gas lamps with electric ones. He was going to build an entirely new infrastructure. He was fighting the gas utility, and he wanted to bury power lines to make electricity invisible, inevitable, and essential.
And Edison had pulled together a crew of phenomenal investors from the New York elite to fund this wild enterprise. This included JP Morgan and his partners and Vanderbilt's son-in-law. But before he could wire the city of New York, he needed a testing ground. And it turns out JP Morgan quite wanted to be that testing ground. And his private house became the first to have electric light. Edison's team went in and installed a generator, its own private generator, in the cellar of his brownstone. And running the generator was so loud and noisy that it shook the walls and terrified the neighbors, and he had numerous complaints. So Edison's team had to keep going out to Morgan's house to resolve issues, but Morgan never wanted it ripped out. He kept persisting.
And Edison's vision was not to build house-by-house electricity. No. He wanted to light up the entire country, and he knew the only way to do that was to build a larger plant that could pipe electricity around town, similar to how coal gas providers had done.
And so together with Morgan, they bought a set of buildings on Pearl Street in Lower Manhattan, New York, to build out exactly that vision. And this was a phenomenal feat. They had to go mile by mile underground through New York City. And so in this 1 square mile radius, they wired up offices, shops, and even the offices of the New York Times.
And so once this was all wired up, September 1882, 3 o'clock in the afternoon, they throw the switch on Pearl Street, and 400 lamps flicker to life. The New York Times building reported having soft, mellow light that was grateful to the eye.
It's a huge moment. It's the first time that there's really a utility scale deployment of light. Morgan's mansion and Pearl Street are separated by these two different visions of what electricity's future would look like. The mansion was this bespoke custom installation for the richest man in America, his own private generator and electrical system. And Pearl Street was the first utility, a system designed to serve a whole region. Its real innovation wasn't just the generator inside, but it was this idea of the whole system. Edison and his team had to invent the wiring, the insulation, the junction boxes, the meters, the safety fuses, even the design of the way that the lights screwed into the light sockets. They had to invent the entire electrical distribution stack, piece by piece.
And this was all motivated by a vision that electricity would change the world if it became infrastructure. So at Pearl Street, he didn't just sell light bulbs, he sold metered lamp hours. You didn't buy electricity as a commodity, you bought into his system. And he very intentionally set the rate at the same cost per hour as gaslight because he wanted switching costs to be zero. In his mind, if the light was better and the price was identical, the gas companies would have no argument.
The question now is whether this direct current system was the only way or the right way to deliver this at scale. Let's talk about the alternative, alternating current. And it's worth pausing on what's actually happening inside a wire. Because most people picture electricity as these electrons racing from the power plant all the way to your house. That's not what's happening at all. In direct current, or DC, the electrons do drift forward, but incredibly slowly, maybe an inch per minute. In alternating current, or AC, they don't even go anywhere. They just vibrate back and forth in place 60 times a second. In both cases, what actually moves fast, almost near the speed of light, is the energy itself. So let's bring AC onto the scene. And halfway around the world, a young, quirky Serbian engineer named Nikola Tesla was having visions of something completely different.
This 26-year-old engineer is walking through the Budapest park, and he's allegedly reciting poetry to a friend when he freezes. He grabs a stick and he starts frantically drawing in the sand. See my motor here. Watch me reverse it. His eyes are wild, images flowing through his head. His friend thinks he's having a nervous breakdown. Isn't this beautiful? Isn't it sublime? Isn't it simple? Tesla's almost crying. I have solved the problem. I can now die happy. But I must live. I must return to work and build the motor so I can give it to the world. What Tesla saw in that moment was something that had eluded every electrical engineer on the planet.
Early motors are much more mechanically tricky devices. And so, how did the early DC motors work? Well, there'd be a stationary outer magnet that creates this magnetic field inside and a wound coil that sits on a rotating shaft. The DC current flows through that coil inside the motor, and the magnetic force pushes it. But to keep the rotation continuous, the current direction through that coil must flip every half turn. Otherwise, the coil would just toggle back and forth, back and forth. And so the way that you do that is you have actual brushes inside and what's called a commutator that enable the current to flip directions each time that it turned a half turn. These brushes are in contact and they're constantly sparking and rubbing as the motor runs. And so a motor that could run on alternating current without commutators, without brushes, without the contact and touching would be a much more efficient and almost magical device. It's like a maglev train. There's just no physical contact between any parts.
Amazing. And so by using two alternating currents, slightly out of phase with each other, you create this invisible rotating magnetic field. It's a wheel of pure electricity spinning in space without the moving parts to wear out. Tesla had just invented the polyphase AC motor, a breakthrough that would make alternating current practical for the world. He just needed to find someone who could understand what he'd created and take it to the next step.
It was not going to be immediate that Tesla might find that partner. In June 1884, Nikola Tesla steps off the boat in New York City. He's got 4 cents in his pocket, a book of beloved poetry, and a letter of introduction to meet the most famous inventor in America. And so when he finally meets Thomas Edison, he's amazed and excited. Here's the man who's revolutionizing the world. But that admiration didn't last long. Tesla went to go explain his revolutionary AC design to Edison, thinking that Edison would embrace the design in him and say, like, well, let's go do this. And the exact opposite happened. Edison immediately cut him off and was blunt. He said, alternating current has no future. It's a deadly current, and anyone working on AC was wasting their time.
The fundamental problem was how these two men approached their scientific discoveries. Tesla later described Edison's approach as if, needing to find a needle in a haystack, he would examine every single straw like a diligent bee until he found it. And to Edison, Tesla was just this poet of science. His ideas were magnificent, but utterly impractical. And so his mind operated in a different frequency.
Edison's mind operated directly, and Tesla's operating at a frequency. Sounds like a good tee up. But despite this, Tesla needed a job and he's liked working in electronics, but he lasted less than a year and ultimately left this job exactly as he arrived. He had almost no money and he just had his ideas in his head and he still was just looking for someone to collaborate with him on this wild AC motor. So Tesla leaves, forms his own company, but it doesn't go so well. He's not quite the best business mind.
Yeah, so his investors wanted simple arc lighting for their New Jersey town, not these revolutionary motors. But he pushed for his AC system, and the investors pushed him out, took Tesla's patents, and Tesla received the hardest blow he could imagine. He went from this premier inventor to a ditch digger overnight.
And so this was a tough period for Tesla, but through some luck and charisma, he ultimately found himself an investor to go at it again. And so in the spring of 87, the Tesla Electric Company was born. He left the ditch, set up his lab, and he was just a machine. He unleashed this whole new AC system at once. Over the next year, he filed over 40 patents covering the motor, the polyphase AC system, generators, transformers, the transmission system, all in one go. He had blueprinted an entire alternate universe of alternating current. And so now that Tesla had a vision and patents, he just needed someone to build an empire with.
Enter George Westinghouse, the inventor and industrialist who, by the mere age of 37, had already built an empire, inventing a train braking system that revolutionized the entire railroad industry. He had also developed track switching and signaling systems, and even safer piping of natural gas through cities. This was a man who had a pattern recognition of understanding transmission over distance. And so in 1885, Westinghouse is reading about a French inventor's secondary generator and immediately sees the analogy to his own high pressure gas transmission businesses. He's thinking, pump something at high pressure and then regulate it down locally. Westinghouse saw this transformer as the missing piece, a device that could step voltage up for long distance transmission and then step it down for safe use. The implications were immediate for him.
So here's where I think we need to talk a little bit about distance and the physics of distance and electricity. While DC was powerful and Edison had figured out, as he put it, subdivide the light, it had two fundamental connected problems. One is that the voltage that leaves Edison's plant is the same as the voltage that arrives at the house or the factory. So you can't do different voltages for different devices. Everything gets that same 100 volts for lights and for the motors, and that can cause limitations in what you can do. But the bigger problem was one of power losses. So there's two simple equations that play out here. The first is that power losses is the square of your current times the resistance in the wire. And the second is that your current equals voltage divided by resistance.
So, what you're telling me is that given a certain wire has a certain resistance, you can't really change the resistance unless you change that physical wire. Really, the thing you can control is current. And if you drop the current as low as possible, you reduce the loss to heat. And if you want to reduce power loss, you adjust the voltage. And because the relationship is current squared, every 10x increase in voltage is a 100x decrease in power loss.
That's exactly right. So if only there's a way to change the voltage up and down when you wanted it. And unfortunately for DC, there wasn't. And so let's talk about the magic of the alternating current transformer. The AC transformer is this beautifully simple concept. You have a iron core bar, and you have two coils of wire on each side. One coil of wire is coming in with the AC electricity, and the other is coming out. And so that first wire coming in wrapped around is inducing a changing magnetic field inside of the bar. And then the other side, that changing magnetic field is inducing a current coming out. And if you have the same number of coils on both of those wrappings, you end up with the exact same voltage in, voltage out. It's just this almost like invisible transfer of electricity from one coil to the other without them touching. Still very cool. But then the magic is if you have a ratio, let's say a 10-to-1 ratio of coils where 100 turns coming in and 10 turns going out, you end up with a 10-to-1 step down. So you can turn 1,000 volts in to 100 volts out.
And so you've changed the voltage without power loss?
That's exactly right. Energy is entirely conserved in this process. And all of this only works with alternating current because you need a changing magnetic field to induce a voltage in that second coil. DC creates a magnetic field, but it's static. It's not fluctuating back and forth. So you can't transform it in the same way. And this has huge implications for the future of alternating current. Without this transformation, you can't do high voltage transmission. And without high voltage transmission, you don't get much of a grid.
And this is why Westinghouse's mind was transforming reading that report. He's thinking, well, what if you didn't need a power plant on every corner? What if you could put generators in one city and light up another city? What if distance becomes irrelevant? Within months, Westinghouse had redesigned the clunky European transformer into something that could be mass produced. And that's what you see coming into the neighborhood to step down that voltage on your electrical poles. And by January of 1886, the Westinghouse Electric Company had incorporated. 2 months later, his first AC power station went live in Great Barrington, Massachusetts.
And the launch was pure Westinghouse. No press releases, no demonstrations for dignitaries. The local paper just noted that the new electric lights were so powerful and so perfectly white. What a different approach than our friend Edison. But Westinghouse had money from his successful businesses, he had the manufacturing capability, and he had the mindset and the desire to win and drive scale. But he was missing one thing. The transformer could now move power efficiently, but at the other end, you still wanted motors. And AC motors didn't really work. Not yet, anyways.
So in 1888, Tesla steps up onto the podium at the American Institute of Electrical Engineers and introduces, in his words, a novel system of electrical distribution and transmission of power by means of alternate currents, affording peculiar advantages, particularly in the way of motors. The engineers in the room had never seen this before. AC motors starting and stopping without those brushes and sparks, creating rotation through pure electromagnetic fields. It was exactly what he had sketched out in that park 6 years ago.
And now we had the whole system, efficient AC motors that could also be AC generators, being able to be stepped up and stepped down and transmitted across long distances. And Westinghouse did not hesitate. By July, he's writing Tesla a check. It was very simple. He said, if the Tesla patents are broad enough to control the alternating motor business, then the Westinghouse Electrical Company cannot afford to have any others own those patents. Tesla's patents mapped out the entire ecosystem, everything Westinghouse needed to build a true competitor to Edison's DC empire. As we've seen throughout history, genius and business sometimes make uncomfortable partners. And so Tesla spends about a year in Pittsburgh trying to make all of this work. And of course, he clashes with all the practical engineers. And meanwhile, back in New York, Edison watches the alliance form with growing alarm. The AC DC war is about to kick off and get ugly.
So our friend Edison has a reputation in America at this point. He is the greatest inventor. And that gave him something very powerful, the public trust. He decides to weaponize this trust and write an 84-page pamphlet simply titled Warning. And inside this pamphlet, Edison's calling alternating current the executioner's current. He details gruesome workplace deaths, linemen being burned alive, workers brushing against AC wires and dying instantly. Behind the scenes, he was supporting demonstrations. One famous demonstration brought a large black retriever on stage, and they shocked him with direct current. The dog yelps, but survives. Then he applies AC current, and the dog dies instantly.
And so this is just getting hotter and hotter. By November 1889, Edison has dropped all pretense of objectivity. He writes, "My personal desire would be to prohibit entirely the use of alternating currents. They are as unnecessary as they are dangerous." This campaign reaches a grotesque climax in August of 1890 when a William Kelmler is convicted of murdering his lover with a hatchet, and he becomes the first person to be condemned to be executed by electricity. So Edison had turned electricity into an instrument of execution. He even tries to call death by electric chair being Westinghoused. But why is he so desperate to stop the march of alternating current?
All of these men, Westinghouse, Edison, Tesla, they had visions for transforming the country. Billions of dollars were at stake. The transformer was AC's secret weapon. It was a fundamental unlock. AC's ability to transform voltage allows it to move over long distances and sets the stage for an infrastructure that we will all now call the grid.
AC's central plants required 1/3 of the copper of DC systems, and this was an era when copper costs could make or break profitability. This alone sealed DC's fate. Just 1 year after Westinghouse started selling AC systems, he had 68 central stations built or in progress. Edison, after 8 years, only had 121.
The war of the currents was becoming a rout. Edison's desperate public stunts couldn't overcome simple math. AC delivered more power, further, and cheaper.
So by 1889, Edison Electric's own subsidiaries were starting to lobby to add AC power transmission to their systems. And so Edison was becoming marginalized inside of his own company. He told the president that he thought it was time for him to retire from the business. And then their lead investor, JP Morgan, viewed that a competitor, Thomson Houston, looked to be the stronger of the two companies. And Morgan, as we know, never one liking competition, put together a merger and called it just General Electric. Thomas Edison was not even aware of this deal until the day before it happened. And I think this moment marks the end of the War of the Currents, and AC had clearly triumphed.
In 1893, America threw itself a party at the World's Exposition in Chicago, and it was meant to symbolize that the United States had arrived. Westinghouse sets out to build the largest AC station ever created, which ends up being 25 times larger than anything that existed. And so in 1893, President Cleveland presses the golden telegraph key. A steam engine roars to life and electricity surges across the grounds, showering the city in white light. 27 million people walk through, and the future of the electric grid is now tangible. Within a year of the fair, AC power had captured 50% of the electricity market.
So, in addition to the party that was happening in Chicago, there was a realization of a massive economic opportunity. People had long admired the immense power of the waterfalls of Niagara and wondered how those could be someday harnessed for industry. But a quick pause before we jump into the Niagara story, because we're about to swim in the units of volts and watts, and so we thought it'd be important to anchor on what exactly they mean and how to think about them. Well, a volt, named after our friend Professor Volta, is a measurement of essentially the pressure of electricity. How hard is that electricity pushing through the wire? So a AA battery is 1.5 volts. Your wall outlet, 120 volts. A generator is putting out tens of thousands. And the big transmission lines we're about to meet in our story are hundreds of kilovolts. Now, a watt is a measurement of power being delivered, named after a hero from our coal story, James Watt. An LED bulb runs out at about 10 watts. A microwave pulls about 1,000 or 1 kilowatt. From there, every step in naming is 1,000 times bigger. So you go from a kilowatt to a megawatt, which powers roughly 1,000 homes. Then to a gigawatt, that powers about 1,000,000 homes. So volts are a measurement of how much pressure the energy is pushing at, and watts are a measurement of how much power is being delivered at any given moment. And so back to our story. So in 1891, there was an exhibition in Frankfurt where German engineers did something that Americans at the time thought was impossible. They stepped up power all the way to 25,000 volts or 25 kilovolts, 10 times higher than anything attempted before, and sent it 175 kilometers from a hydroelectric plant back in Laufen.
Transmission.
Transmission at a big distance. It's possible. Back in the US, 103 of the nation's richest men made a huge bet. They pooled $2.6 million, a massive amount of money for the time, to build a power plant that could harness the power of Niagara Falls. Funny enough, they didn't actually know yet how they were going to harness that power. There were proposals to use rope, water pressure, air pressure. They weren't quite sure. So what did they do?
A project this size requires minds from all over. So they announced a global competition and invited the world's best engineers. 6 companies made the cut, 3 from Switzerland, 3 American. Our American firms, Westinghouse, Thomas Houston, and our old friends, Edison General Electric, were in the mix. Now, we're talking about a project digging 200 feet beneath the Niagara Falls. The scale here is enormous. And they're building infrastructure for generators that would produce 100,000 horsepowers. Just to give you context, that's equal to every central power station operating in America combined. One plant to match the entire nation's electrical output.
Westinghouse actually won this contract as well. He and Tesla would be the ones to build the AC generators. After all the demonstrations, all the debate, all the corporate warfare in America, this was the test that finally mattered. Could AC power travel far enough to be economically useful at scale? And that system was absurdly ambitious. Electricity would leave Niagara at 2,000 volts, get stepped up to over 10,000 volts by these massive room-sized transformers, then flash across 26 miles of transmission cable to the industrial Buffalo.
And so in 1896, they flipped the switch. Power surges from Niagara to Buffalo, and it works. Buffalo streetcars are running on water falling 26 miles away.
This was the proof that everyone had been waiting for. Long-distance AC transmission, not just as a demonstration, but at commercial scale. The single success completely reshaped America's geography of power. Suddenly, electricity did not have to be generated exactly where it was going to be used.
This unlocks the ability to disconnect geographical generation from the place of consumption.
So this first plant at Niagara produced 11 megawatts, which was nearly 20 times what Edison's Pearl Street station had produced.
Now, up until this point, we're talking about electricity primarily used for lighting. That was the clear consumer use case. But the level of power coming off of something like Niagara was now fit for factories. So what would the electrification of manufacturing look like? Well, in 1902, only 5% of industrial power came from electricity. But within 14 years, that number exploded to 40% of industrial power. The scale of transformation ahead would require something that sounded, as one banker put it, like astronomical mathematics. $2 billion of new capital.
If you walked into a factory in 1900, It'd just be this forest of belts and pulleys that are overhead the factory floor. They ran the length of the building, powering every machine through this maze of leather straps. And the industrial power would come from a central steam engine in the room, driving this whole mechanical belt system. But by 1920, factories consumed more electricity than all other users combined, more than every light bulb in every home and every street in America. And the investment in scaling up was significant. That $2 billion, that's $61 billion in today's money. Only the railroads of the time had demanded investment on that scale. And that cheap electricity started to enable new things to be made that had never been made in the same way. Let's talk about aluminum.
So, aluminum back in the early 1900s is not what we think of today. 130 years ago, aluminum cost $15 per pound, which was more expensive than gold or platinum at the time. Napoleon III reportedly saved his aluminum dinner plates for his most honored guests, while the lesser nobility ate off of mere gold plates.
And that was about to change. A young American, Charles Hall, and a Frenchman, Héroult, designed a new process called the Hall-Héroult process to dissolve aluminum oxide and then run massive amounts of current through it. It's an insanely electricity-intensive process. Smelting a single ton of aluminum now takes 13 to 15,000 kilowatt hours of electricity, enough to power an average American home for over a year. There's a joke in the aluminum industry that aluminum is really just congealed electricity.
And so the scale and transmission of power generating from the Niagara Falls created opportunity. The reduction company moved from Pittsburgh to access this power where electricity cost almost nothing. And using that cheap power, his company, which became Alcoa, brought aluminum's price down to below $1 per pound.
It's a 15x reduction.
It's crazy. You're talking about a precious metal becoming an everyday commodity in under a decade.
From Napoleon's dinnerware to our sparkling water cans. And after the large industrial loads, a second large consumer emerged in the form of rail. In 1887, America had 35 miles of electric streetcar rail. By 1902, more than 800 systems ran on 22,000 miles of track. So the nation was being completely rewired between projects like Niagara Falls, the growth of central generating plants, now 3 large users from lighting, industrial manufacturing, and streetcars. It was in a moment of explosive growth of possibility of what you could do with electricity.
And with this possibility, finance is flowing in and engineers just keep pushing the boundaries. Transmission voltages climb from 60,000 volts being transmitted around 1900 to over 280,000 volts by the 1930s. Each increase meant power could travel further, connecting more factories, more cities, and more opportunity.
So with all this innovation and scale, I think we haven't really answered the question of what is the business model that actually underlies this growth? How does this come to be?
Well, Ben, you want to go to Chicago? This is a 300-person trading post in the 1830s that balloons to over 1 million people by 1900 and becomes the fastest growing city in America. It also had to rebuild itself after the Great Chicago Fire of 1871, which led to the world's first skyscrapers. This booming city is the Chicago that one Samuel Insull enters.
And so this is the era that we think of as the birth of the utility. And so who is Samuel Insull? Well, he is arguably, I think, the most consequential individual person in the story of the grid. He didn't invent the motor, the transformer, or some other physical element of the grid, but he invented the entire business of power. He would go on from being the hero that brought electricity to America to later being one of the most hated tycoons of business. But we'll get to that in a couple decades. So back in 1881, he arrives in the US, a young 21-year-old coming from Edison's London office, and he quickly became Edison's personal secretary. Remember, Edison was this crazy hard-driving guy who would sleep for 4 hours at a time at the office, and Insull matched him hour by hour, always being available at his beck and call to pull off what the boss needed.
Boss wanted copper at 2 a.m., Insull was there to make the order. And so a few years into it, they were running out of factory space. And Edison had trusted Insull so much that he sent him to this factory in Schenectady with some simple instructions. He said, "Do it big, Sammy. Make it either a big success or a big failure." And Insull took this factory from 200 employees to 6,000.
So if you remember, Edison General Electric had been merged by JP Morgan to its competitor and became the behemoth General Electric, this $50 million market cap business. And they offered Insull a top spot with a massive salary. His future was all set. Did Insull accept the job?
Insull shockingly said no. He stuns everyone and instead chooses to go to Chicago Edison, a company worth less than $1 million that offered a third of the salary. Everyone thought he lost his mind.
But Insull looked at the emerging General Electric, which was focused on the manufacturing of machines, the dynamos, the transformers, selling them to whoever would buy them. And he thought the future was not in making the dynamos, but in what you did with them and building the systems that would deliver electricity to millions of people.
He understood a few key things in this moment. First of all, electricity has massive economies of scale. The bigger your system, the cheaper your kilowatt. Second, he understood that connecting isolated plants into networks created exponential value. And third, he realized that you couldn't build this infrastructure piecemeal, like custom machinery. You had to step back and think about it in mass production. These are all themes that are going to reverberate through the next few decades.
And the big barons of the age moved fluidly between railroads, telegraphs, and now electric power. They all understood that the real money wasn't in some particular technology, but in the networks that the technology enabled and finding ongoing ways to provide and extract value from the emerging growing network that you've built out. So Insull left the safety of manufacturing for the chaos of Chicago Edison. Chicago Edison, was it a massive utility? No. It was 5,000 customers in a city, this booming city of a million. And this plant that they'd built and invested tremendous amount in was running at a massive 5.5% capacity.
Insull's just an operator at heart. He understands businesses inside and out. He immediately told his investors, if your entire plant is only in use 5.5% of the time, the only question is when you'll be in the hands of a receiver. Your plant is sitting idle 94.5% of the time. This problem was fundamental because electricity is not like any other commodity, right? Unlike coal or oil, electricity can't be stored. Every kilowatt that you generate has to be consumed in the instant that you generate it.
Let's just emphasize this point a little bit more sharply because this echoes through to today, which is the moment that electricity is generated, it needs to be consumed. And that drives so many fundamentals of the business of the grid.
And so that means that power plants were already being sized for what they understood to be peak demand. That means that those few hours, typically from 6 p.m. to 10 p.m., when everyone had come home from work and turned on their lights, was the maximum power being consumed. So your plants had to generate that much. And here's where Insull saw the opportunity. The same temporal constraint that was killing his business could actually be the way he saves it. If he could find customers who needed power at different times, he could then utilize more of the power he was generating. This wasn't a technological breakthrough. It was just an orchestration of demand based on the different customers that he could acquire.
So he went hunting for those large loads that could balance each other out. His first target was Chicago's electric streetcars. They needed massive amounts of power in the morning and in the evening when they were moving commuters, but almost nothing midday when those commuters were over at work. And they peaked exactly when residential demand was lowest.
Next comes the meat packers. Chicago's stockyards were relying on ice harvested from Lake Michigan. But with electrical refrigeration, you could have around-the-clock cooling. And so 24/7 loads were a great customer for Insull because they kept his generators humming through the dead of the night.
Those sweet, sweet base loads that will also echo through to today. Then Insull looked up and you had Chicago having skyscrapers. Inside those towers, there's effectively rail cars that are going vertical. So those elevators ran all day during the business hours, again, when people are not at home using the evening lighting.
And this guy is just idea after idea. So he forms the Federal Electric Company to, get this, manufacture and lease electric signs. He invented signing as a service, where he would give you the sign essentially for free so that you would have to pay monthly electrical bills on the lights you used on those signs, creating overnight illumination and adding to those nighttime baseloads that he needed. And so by 1910, the Chicago Edison's load factor, which remember we said was 5.5% and would have bankrupted the company, was now over 50%, amongst the highest in the nation. Insull had just solved this puzzle of time through orchestration of different customers utilizing electricity that was generated in that moment.
To echo through to today, I think he discovered or invented what we now call the platform effect, which is the idea that the same infrastructure could be used by many different types of customers and make it wildly profitable when you amortize that infrastructure across many people. Sounds a lot like AWS in the cloud now.
So there are different ways to build a big user base. And Intel did something that shocked everyone, especially his board. He started cutting Chicago Edison's electricity rates from 20 cents to 16 cents per kilowatt hour. And then he cut them again and again and again. By 1909, his rates had plummeted to just 2.5 cents, almost 90% drop over the course of 12 years. His competitors thought this was suicide.
This is what Jeff Bezos would discover a century later. Sometimes the way to make money is to stop trying to make so much money. And if you make electricity cheaper, you can make the market bigger, much, much bigger.
Insull realized that in the electricity business, capital costs are everything. His turbines cost the same whether he runs them at 10% of the day or 90% of the day, because fuel costs were almost a rounding error at that point.
So his competitors were treating electricity like champagne, this like luxury product with luxury pricing that only the rich can have. Insull thought it should be water, something that everyone should have at the lowest possible price. And this is a real like inversion of the common perspective that monopolies should charge higher prices for a luxury product. We're going to go from only JP Morgan having lights at his house to everyone having abundant electricity.
What an amazing impact on society that this decision had. And so every time Insull cuts the rates, he makes the headlines. His customer numbers grew from 5,000 when he arrived to 200,000 by 1913. He had gotten to a tenth of Chicago's entire population wired into his network.
And he started to do interesting creative things with pricing. So households would pay a fairly low 3 cents per kilowatt hour at this time, but major industrial loads could run factories at night for less than a penny per kilowatt hour.
In 1902, it took about 7 pounds of coal to generate a kilowatt hour. 30 years later, he just needed a little over a pound of coal, an 80% improvement that he passed on directly to consumers instead of building his profit, because his motive was to gain adoption and spread access. So you have this wonderful flywheel developing. Larger generation plants drives more efficiency. More efficiency reduces prices. Price drops brings in more customers to the grid. And enter Javon's paradox. The lower the prices, the more people use it.
And so in 1907, Insull leveraged this success for his biggest move yet. He proposed merging Chicago Edison with his other large rival there, Commonwealth Electric, promising that he'll drive even lower rates in exchange for consolidation and approval. And so this combined force, Commonwealth Edison, would eventually serve 70% of the state of Illinois. And this strategy was working beyond anyone's wildest dreams, but keeping those prices low while demand exploded would require massive technological innovation. Insull's steam engines were reaching their physical limits. They're getting too big, too loud, and too inefficient for the scale that was about to come next.
These steam engines that you're mentioning, it was a reciprocating engine, had hit this wall. And so Insull needed something radically different. And so here he makes a bet on an unproven piece of technology and putting all his chips on the table behind the steam turbine.
Yeah, and if you want to go deep on this, I recommend listening back to our coal episode because we talk about the wild story of the invention of the turbine. But in short, Charles Parsons of the UK had invented this steam turbine back in 1884 for naval use. And almost 20 years later, no one had proven that it could work at the scale that Insull now wanted. The first turbine he demonstrated was a 7.5 kilowatt turbine, barely enough to power a small building.
7.5 kilowatts ain't going to cut it. Insull teams up with GE to build a 5 megawatt turbine. And he takes a massive development risk because he had an intuition that the larger these turbines get, the more efficient they get, which was a perfect fit for his high volume, low price strategy.
And it worked. When the first turbine spun up at Fisk Street Station in Chicago, it didn't just work, it transformed the industry overnight. This new unit produced twice as much power as any steam engine ever built.
And this was no secret. Within a year of Insull's order, other American utilities had ordered hundreds of thousands of kilowatts worth of turbine capacity, and engineers were traveling from all over the world to see what Insull was doing. It was the age of the turbine.
And they just kept getting bigger and bigger, exactly as Insull had hoped and bet on. And so you just got compounding value of scaling larger and larger.
So, alongside the increase in turbines, you have access that's spreading, you have costs that are lowering, and you have another challenge that's brewing under current. In the 1900s, it's the progressive era. We're talking about reformers who want vital services like water, gas, and electricity to be public goods and not run for profit.
A new Chicago mayor who was just elected in 1905 ran on this platform of immediate municipal ownership. He was going to push for the city to take over the streetcars and then the electric grid next. And this was a huge threat to Insull's dominance. In fact, between 1896 and 1906, the number of municipally owned electric plants had quadrupled. Insull realized that if he didn't provide an argument against this, a better alternative, the public would eventually vote to nationalize his company. And so here's where Insull pulled off a masterstroke. Instead of just fighting head to head with progressive era reformers who wanted to battle every monopoly, he offered them a grand bargain. He said, "You let my companies have exclusive territory, and in exchange, you government can regulate our rates and our profits, and we'll be under your control."
And this argument to convince the reformers was predicated on the idea that electricity was fundamentally different, that competition in power generation will actually harm consumers. So Insull is essentially going public saying, please regulate me so I can consolidate. And he turns this movement and the government from an adversary into a business partner.
And the idea started to take off across the country. Wisconsin, Massachusetts, and New York took the first deals in 1907. Within 9 years, 30 more states had jumped on board with this regulatory model. By 1915, 41 states had utility commissions that were setting the rates based on what was termed actual costs and a reasonable profit margin.
So, why are the progressive reformers in this unlikely alliance with a monopoly? Why were different states adopting this? Well, for the simple reason that Insull was delivering results for society. We talked about this massive price drop from 1890 to 1920. Electricity costs fell 80%. And so, even if you have this theoretical argument against electricity being profitable and should be a public good, you couldn't argue with the fact that more and more people were getting cheaper and cheaper power, and it was transforming their lives and transforming the American economy.
And a lot of this was an argument against waste. The idea was, let's stop running multiple lines throughout a city. Let's drive that inefficient waste out.
And for utilities, this was politically brilliant. It ended the constant shakedowns from city governments threatening municipal ownership, as we talked about. And it created one set of rules, one regulator, and guaranteed profits. And this is the introduction of the term that we still hear today, the natural monopoly.
And by the mid 1920s, the entire industry had bought into this vision, and almost nobody would imagine managing electric power with anything other than this kind of regulatory monopoly construct. This was a complete reversal from how it was in 1900 when you had multiple competing folks trying to electrify people's homes in different standards. Insull had won. He'd convinced America that competition was actually harmful for them and that his monopoly could serve the public better than the free market could.
So, this is the market structure that Insull almost single handedly created. Alongside larger generation, dropping costs, and adding these variety of customers, you also had the electrification of the roaring 20s inside the home. In 1907, about 8% of Americans had electricity, mostly the wealthy urbanites. By 1920, that jumped to 35%. And by 1929, 70% of American homes were wired.
That's like the smartphone adoption curve. Like, think about it. You enter the 1920s, it's like entering 2008, 2009. Almost no one has a smartphone. Everyone's got their razors. And by the end of 2018, everyone has an iPhone or Android. That's what this decade was like with electricity. You entered 1920, one of your friends might have some electric lights. By the end of the decade, almost everyone does.
Now, it's worth taking a moment to just unpack what having electricity means. Let's call it 1915 and walk through a home because it's not anything like you or I can imagine.
Yeah, so these power lines come in to your basement, two wires. They hit a wooden board that's mounted on a wall, and on that board is called a knife switch. It's a literal blade of copper that you grab and slam down to connect power to the house. Maybe a couple screw-in fuses, and that's it. That's your whole electrical panel.
And from that board, you've got wires running through ceramic tubes and porcelain knobs that serve as insulation. This knob and tube wiring was all you had. No grounding, no insulation, just bare copper conductors separating your wood frame house from your wires with just a bit of air and some porcelain.
And those wires are not going to wall outlets. They're just going to built in light sockets in the ceiling. There's no wall outlets, no standardization. It was all built for lighting.
Wait. You said in the ceiling. So it's 1915, and someone just convinced you to buy the new GE toaster. Well, how are you going to use it? You have to go and unscrew your light bulb from the ceiling, screw in an adapter, and run an extension cord down to your kitchen table. If you want toast, you're sitting in the dark.
Yeah, you just unscrew your light and you might like shock yourself just screwing in the toaster.
Yeah. If you're one of the lucky people, you've got a two-part adapter. And so one piece stays in, screwed in, and now at least you can keep the light on while you're toasting your bread.
And of course, if you put in too many devices, you're going to blow a fuse. And if you're out of fuses, you might stick a penny in to bridge the connection in a very dangerous way and overheat your knob and tube wiring and burn your house down.
Yeah. It's almost 30 years, like an entire child's lifetime grown up and leaving the house, that you get to electricity to having like wall outlets where you can run a toaster, a vacuum, a radio, and your iron plugged into the wall and not blow a fuse.
That period of the 20s is when this came to be. It's all, again, like the smartphone period of the mobile device, when all of the standardization started to happen, the wall outlets, the circuits that actually made this a really consumer friendly technology.
And so you go from maybe a light bulb to the average home having 7 to 11 electrical appliances in it. Well, this adoption didn't just happen magically, right?
No, there's huge companies wanting you to do this. So they started to get together and build a advertising campaign against the slogan, electrify your home, publishing checklists of appliances and what a modern household could look like.
You got GE, Westinghouse, every utility putting out magazine ads in the Ladies' Home Journal and Good Housekeeping, very specifically targeting women, promising electric irons and vacuum cleaners and washing machines to replace the drudgery of domestic labor.
And the pitch was very explicit. It said electricity would be your willing electrical servant, your tireless employee who never complained, never quit, never needed a day off. It kind of reminds me a lot of Claude Code right now.
And of course, you can't have a massive marketing campaign without a financing arm alongside it. And so consumer financing and installment buying gets pioneered in this area. So you can buy your $150 washing machine on credit for a few dollars a month.
What an amazing point. You can imagine now the flywheel of standardization, invention, and credit just driving the 20s into that roar, right? Into this exciting moment of you are upgrading the home in all of these, magical ways.
Your home is an entirely different place to live during this couple decades.
Absolutely. And guess what? You turn then to the factory where you're at work, and it's the same thing. Electric power per industrial worker increased 30-fold between 1900 and 1925.
And so by 1930, electricity provides 80% of all industrial mechanical power. We were talking about those old leather belts running from steam engines to machinery. That's gone. The factory floor has been transformed. And Ford's assembly line is the perfect example of that.
And other countries in Europe and the UK were also going through their own innovation here, but the US was dominant in its scale of adoption. The US was generating and using more electricity than the rest of the world combined when you enter 1929. This wasn't just a boom time for the electricity industry, it was a boom time for Wall Street. And utility stocks became the ultimate safe investment. They called these things widow and orphan stocks because they would be so safe. These companies had legal monopolies over a product that everyone wanted more and more of each year. What could go wrong? Well, the story of Insull's downfall begins when he finds a new interest in the mechanics of finance. You see, in addition to the technical and physical scale-up of his empire, something really changed in him going into the 1920s. He found something intoxicating about growing the financial empire.
Oh man, this guy became in love with debt because his empire was growing rapidly, right? In 1912, he had about $90 million of assets. 5 years later, he's at $400 million in assets across 13 states, and he was just getting started.
And the secret was his structure. It was the structure and magic of the holding company. Financial innovation that was brilliant, dangerous, and technically legal still at the time. How it worked is he'd create a company that existed solely to own other companies, then another company to own another company, layer upon layer upon layer.
And you just lever that puppy up. A dollar invested at the top of the pyramid can control $10, $20 worth of power and equipment at the bottom of that pyramid. It's financial engineering pushed to the limits.
So by the end of the decade, in the late 1920s, his empire had become incomprehensibly vast. He controlled utilities serving over 5,000 towns across 32 states. One out of every 10 kilowatt hours generated in America flowed through one of his companies.
My man's sitting on top of a house of cards. He's chairman of 65 companies, president of 11, director of 85 others. I mean, just keeping track of all the board meetings must have been a full time job.
And of course, his wealth was exploding with his empire. In 1927, he was worth about 5 million. Comfortable, but not spectacularly noteworthy for the age. Going to the run up of the market, it had multiplied to 150 million in just 24 months. This financial engineering had made him one of America's richest men.
And the game that he played, it's next level. He had every employee become a stock salesman. So your meter reader would check your electricity usage and then knock on your door and try and sell you shares of the company. I mean, it's like a Comcast technician pitching you stock while installing your cable.
And this became the way that the entire utility industry played out. By the early 30s, just three holding companies would control over half of America's electricity generation: JP Morgan's United Corporation, GE's Electric Bond and Share, and Insol's Empire. And so we're getting to the end of the 20s into the 30s, and you got a big, highly levered house of cards. You're selling stock door to door while you check people's meter. What could possibly blow over the cards?
If I remember correctly from US history, October 1929 is when the things start to fall apart. So you get the stock market crashes. Insol's empire is levered 30 to 1. So this financial engineering that sent him on explosive growth was now working very quickly in the inverse direction.
And this is the first time that electricity usage also started to really decline, right? You're shutting down factories. People are not going to work. People are trying to save money. So consumption drops 23% that year.
And Insel, as astute of a businessman that he was, didn't believe that this crash was as big as it was. And so he just continues investing and even trying to take out loans. And by 1932, his Midwest Utilities enters receivership. This was one of his flagship companies. And so his empire just starts to fall like dominoes with all his cross ownership guarantees and web of holding companies.
Within just 2 months, his day of reckoning comes, and this now 73-year-old Insel resigns from all of those 65 chairmanships, directorships, presidencies that single day. His vast $150 million fortune, gone in a second.
Now, a fun quick aside is there's another Chicagoan whose name will reverberate through scandals that we have lived through at the turn of this century, and that's a one Arthur Andersen. Arthur Andersen was actually the audit firm that was assigned to Insol's utility companies. And so when Insol's empire collapsed, it's Andersen that finds the fraud and brings about the negligence of which he was running his companies. And this activity actually helps establish Arthur Andersen's reputation as one of independence and rigor in the profession.
Which held up great until later in our story, you'll hear about a fun company named Enron. Anderson ultimately found that the underlying fraud was that assets had been sold back and forth between holding companies and used to inflate the book value of the companies.
And so Insol becomes the perfect villain for the Depression. FDR is now on the stump and actually calls out Insol in his campaigns as the man who brought electricity to millions was now the symbol of everything that was wrong with the 20s.
So Insol, afraid of going to jail, gets out of town. He flees to Europe, is dragged back at some point, and in 1934 has a trial in Chicago. And he defended himself, still believing, "I've erred, but my greatest error was in underestimating the effects of the financial panic."
As complex as his holding company structure was, and potentially unwise to be fully levered up to that extent, he didn't actually do anything illegal. And so he was acquitted quite quickly.
But that didn't restore his wealth, his reputation, or his mental health and energy. Just a few years later, Samuel Insull dies of a heart attack in a Paris metro station with a few cents in his pocket. And America is left figuring out what to do next to evolve the web that he created. The Depression is about to transform the power industry.
By 1933, the American economy had lost nearly half its value. Production had fallen by 47%. 9,000 banks had failed. The Depression had wiped out the savings of millions of families. And electricity which had been the great symbol of American progress, was actually now tied up in all this wreckage. Headline after headline in the newspaper has exposed how Insull and others had sold worthless utility stocks to ordinary people who thought they were basically buying the safest investment in America.
And so when Franklin Roosevelt took office in March of 1933, it wasn't a question of if they would intervene in the electricity sector. It was a question of how deeply. If ever there was a moment for the government to consider taking ownership of the power plants and the grid, this was that moment, the era of the New Deal.
But Roosevelt had been on the campaign trail, and he had already addressed this a year before. And in his words, I do not hold with those who advocate government ownership or government operation of all utilities.
Roosevelt's position revealed a very pragmatic view alongside progressive rhetoric. He declared, quote, electricity is no longer a luxury, it is definitely a necessity, but also that as a broad general rule, the development of utilities should remain, with a certain exceptions, a function for private initiative and private capital.
And so instead of nationalization, Roosevelt turned to a three-pronged strategy that would shape the electricity markets for generations. First, the federal government was going to embark on major hydroelectric projects that would serve as yardsticks, the public alternative to what would reveal fair electricity prices. Second, he was going to strengthen the hand of municipalities that wanted to create their own power systems. The logic was that the mere threat of public competition would help discipline these private utilities. And finally, he would entirely dismantle the holding company empires, not regulate them, not reform them, but tear them down.
And so, as soon as he took office, they undertook the most extensive government investigation of any industry. In this study, they documented all the systemic abuses, particularly the manipulation of the stock market, how the holding company structure was designed to drain profitable utilities and finance the growth of these financialized empires.
And so the result of this behemoth study was the Public Utility Holding Company Act of 1935, PUCA, which included this death sentence clause on the holding companies. Roosevelt and Congress had decided that these corporate pyramids had to die, and they gave the SEC the power to kill them.
Practically, what it said is that every holding company had to divest assets until it operated as one single integrated system in one geographic area, right? A company could own a grid, they couldn't own multiple dispersed things. No more 10-layer pyramids controlling utilities across dozens of states.
But of course, the utilities are a very large industry. They're not going to lay down. And they fought back with fury. They launched what was probably the largest corporate lobbying campaign to date, bombarding representatives with millions of letters and hundreds of thousands of telegrams trying to defeat this legislation.
They framed the fight as a struggle between private enterprise and big government tyranny.
But in the end, the Depression had so thoroughly discredited the holding companies that the case for destruction was already made. When you're already seen as the villain, screaming louder off the rooftops doesn't really help. And so, over the next 15 years, the SEC ordered the divestiture of tens of billions of dollars of utility assets. And the argument that fueled this was that the operating companies needed to grow to meet the nation's needs that was being accelerated in the run-up to World War II.
And ultimately, the law worked. With PUCA enforcement at its peak and wartime mobilization starting to drive demand, generating capacity was able to still increase 42%. And so now, freed from this holding structure pyramid that drained profits, operating companies actually were able to expand much more rapidly than they had under that constrained system.
And so the PUCA's logic here is very, very interesting and impactful. The Insull-style holding companies were too big and too complex for state regulators to oversee. So the solution was to make them smaller, to force them into these single geographic entities so that public utility commissions could actually attempt to regulate them.
In this moment, this regulatory framework really started to click in.
State-sized regulatory structure has reverberations for decades. But critically, this decision did not overturn the natural monopoly structure that Insull had created to allow for only one utility to operate in a jurisdiction and prevent competition. No, that stayed in place very clearly. This decision worked on top of that just to define the jurisdiction and regulatory authority, almost to a state actor level.
The exception, of course, is when electricity is crossing state lines. What are we going to do about that? And so at the same time, Roosevelt transformed the powers of the Federal Power Commission, the FPC. which today we call FERC. The Federal Power Act of 1935 gave the FPC power over all wholesale electricity sales and transmission that cross state boundaries. And in the mandate, they wrote that rates must be just and reasonable and not unduly discriminatory or preferential. Those 9 words would spawn thousands of court cases, regulatory proceedings, and bitter fights over what exactly constitutes a just and reasonable price.
And this huge act locked in another major conceptual anchor that held up until today, and that is cost of service and return on equity. So essentially, a utility gets to recoup its costs within its exclusive territory and a guaranteed set profit on its investments, all charged to the customer.
The ratepayer in exchange gets reliable service at regulated prices and less market chaos. And investors get these bond like low risk investment returns.
So this entire post-depression bargain was fairly elegant, and it created an understanding of the utility business model that morphed into what is thought of as the regulatory compact, which is no real legal compact unto itself, but is the understanding of these guaranteed returns on top of costs that are set across all these different jurisdictions.
Ultimately, the law was an act of great compromise because full federal retail regulation was politically impossible. You left with federal regulators overseeing wholesale transactions and interstate transmission. State regulators would get to keep control of retail rates and local distribution, and utilities had their exclusive territory with guaranteed returns.
It's wild. You've got the grid, which is a physically interconnected interstate network, regulated as if it were a collection of separate state-sized autonomous systems. It was not necessarily designed as what anyone thought was the optimal structure for interstate network, but the most pragmatic one and the most politically feasible one at the time. And it's also interesting to note that electricity is a bit of an anomaly here, right? Because for decades, the federal government had authority over railroad rates and practices. And soon after this act, gas pipelines were put under the FPC for wholesale interstate regulation, which actually did cover most of the industry because gas is inherently produced in one area and piped to another area. And then the 1956 Highway Act gave federal authority over a network of interstate roads. And so electricity kind of looked more local. Your utility served your city, your state PUC regulated your utility, even though the physics of the grid were more interstate. So the more complex the grid became, the harder it was to tell where your state authority ended and where your federal authority began.
So we enter the early 30s with essentially 2 structures, right? These investor owned utilities that have been co designed with this regulation and battle with the government, and then the continued growth of the munis. When you think about where I am in Seattle, we still have Seattle City Light, where you are and I, right? You have a Los Angeles Department of Water and Power.
That's right.
Those harken back to the alternative model. But both the investor owned utilities and these munis are designed to serve cities. There's still another third of America that's not being electrified at this point.
So let's talk a little bit about this urban rural divide that electricity had exacerbated in America at this moment. So around 1934, a middle class family in LA was paying about $2 a month for electricity. And this $2 got them toast every morning from their toaster, maybe waffles on Sunday, clean clothes from their electric washer, and radio that they could listen to every night.
They're truly living in a different era. Meanwhile, if you get in a Model T and drive 50 miles away, families on a farm were hauling water manually from the wells, washed clothes by hand, and had to go to sleep when the sun went down or light up an old candle or kerosene lantern.
That's right. No washing machines, no refrigeration, no clean lighting. Rural America had none of this. And you had farm families, children studying under kerosene lanterns. The gap between city and country was stark.
To put numbers on it, only 10% of American farms had any electrical hookup in 1934. And that figure was growing very slowly because simply there wasn't the economic motivation for a utility to come and hook them up.
That's right. It cost around $2,000 a mile to string the lines to rural areas. So private utilities needed like 3 or 4 customers per mile just to break even. But if you look at these farming regions, you might only have 1 or 2 customers a mile. And so for the almost 7 million farms scattered across rural America, the math simply didn't work out for them to get a wire.
Math didn't math. And so Roosevelt saw this both as an economic opportunity, but also a deep moral failing. He declared that the isolated farmers were, quote, as entitled to the liberating benefits of electricity as Americans living in cities and suburbs.
And so what did Roosevelt do? He found a one Morris Llewellyn Cook to solve this puzzle. Cook had been pushing for rural electrification since the early 20s, and that he had concluded that private utilities would never serve rural America without strong government intervention.
And so they kicked off in 1935 the Rural Electrification Administration, or REA. And they had a radical idea. If investor owned utilities aren't going to do it, let's let the farmers own the utilities themselves.
The formula was simple. The government would provide 25-year loans at 2 to 3% interest, way below market rates. And the farmers would form cooperatives. Each member would buy shares into that cooperative. So this wasn't a charity. It was the farmers owning the means of their own modernization.
And ownership alone wouldn't solve ultimately the cost problem to make this economical. So REA also helped develop this assembly line construction. They used local labor and they standardized many of the designs to drive the cost down. Classic rights learning law applied. So in just a few years, they slashed the cost of building rural lines from $2,000 per mile all the way down to $600 a mile.
And the speed of this was crazy. By the end of 1938, you had 350 cooperative projects across 45 states providing electricity to 1.5 million farms. So we went from zero to 1.5 million farms electrified in just 2 years.
And of course, this created its own momentum and its own flywheel, right? Just like we saw in the 20s in the cities, electrification drove demand for appliances. Those appliance sales justified more lines, and it became more and more valuable for everyone to have hookup. And that drove costs down, attracting more members, and you get the feedback loop that Insul had pioneered, but now applied to the rest of America.
And the cooperative model also embedded democracy right into the power system. One member, one vote, regardless of how much electricity you were using. And so by 1950, we had a full 80% of America electrified.
And these cooperatives didn't just electrify rural America, they created a third structural alternative to the investor owned utilities and the munis. Today, those co ops still serve 42 million Americans across 47 states. In some of those places, power is the cheapest it is anywhere in the country.
And so the REA and cooperatives solved this important distribution problem, getting power to farms that had power nearby but didn't have the lines. There's another challenge that we're seeing in the grid at this moment, which is what about the regions that don't have any power generation near them at all?
So Roosevelt's come in, he's broken up the failed utility holding companies. He's electrified the rural parts of America that the utilities wouldn't economically wire up. He has one more major act in reshaping the utility industry, exercising the great powers of a government that could build things.
And the Depression had given Roosevelt something that no other president had: millions of unemployed men desperate for work and a political mandate to do something about it.
And so let's talk about the build out of dams. Dams were the perfect New Deal project. They would employ thousands during construction. They would control the floods that had devastated farming communities for generations. And they'd provide irrigation to open up new agricultural lands down in that fertile California.
And we added one more clever trick to this dam building project. They weren't just building flood control and irrigation, but they were building power plants that would pay for themselves. So if you take the Hoover Dam as an example, it was about $50 million for the dam and another $70 million for the electrical generators that were going to be powered by the dam. And the entire project would be paid back through the sale of that electricity.
That's right. And by 1987, power sales had repaid every penny of Hoover Dam's construction with interest.
What a formula.
We built this thing 80 years ago, and it is massive. We used 4.4 million cubic yards of concrete. That's enough concrete to pave a 2-lane highway all the way from San Francisco to New York.
And at this time, it was the largest hydroelectric producer in the world, providing more than 70% of LA's electricity. My city here, the sprawl, the defense plants, the entire Southern California boom, powered by this great dam in the desert.
And of course, getting that power to LA required another marvel of engineering. 280,000 volts transmitted across 260 miles of desert and mountains. We first saw this back in Niagara Falls, but now we're applying it at a whole new scale.
And Hoover Dam is just one of the great dams we built during this era. And what's interesting is how the grid's topology got shaped by water. You had the TVA following the Tennessee River, which we'll talk about in a moment. BPA followed the Columbia River. You had Niagara Mohawk set at the Niagara Falls. So before the dam era, most of electricity was generated at coal or oil plants built near the cities they served, right? Generation and consumption were at the same place. Hydro inverted that. You had to generate power where the river fell and then build the transmission line to where people and factories used it. And so the geography of falling water ended up determining the electrical backbone of America.
Yeah, and out here where I am in the Pacific Northwest, the government doubled down, built Grand Coulee and Bonneville dams. And when Bonneville started producing power in 1938, one New York congressman mocked that the only market for the Northwest electricity was, quote, rattlesnakes, coyotes, and rabbits.
Yeah, because he was thinking of the old version of a coal plant grid located near the cities. The hydro grid is something different, right? It's a network of long lines connecting remote generation to distant load.
And so he couldn't have been more wrong. By 1939, just 1 year later, Bonneville had signed its first major contract. Guess who wanted that sweet, cheap power? Our friends at Alcoa. That same Alcoa that had moved to Niagara Falls wanted to expand out here in the Northwest. Cheap hydropower continued to attract aluminum smelters, and aluminum would become quite important in the years ahead.
And the BPA was serious about this activity. They even hired Woody Guthrie to write 26 songs about public power.
And you know what's funny? Just the other day, my daughter asked me to play that song, Roll On Columbia, for her because apparently her school's doing a little like school performance for a promotional song for the BPA.
Your power is turning our darkness to dawn. Roll on, Columbia, roll on.
Well, as well they should. It's one of the most important institutions of the Western grid. The BPA didn't just distribute power, it connected generation to consumption across hundreds of miles.
And it had a few interesting regulatory details to it. First, BPA gave a preference clause to public utilities and rural cooperatives. Those are those munis and co-ops that got first dibs on the cheap power before any private utility could touch it. So this created an entire network of public utility districts across the Northwest that still exist today. And it's why many in this region pay some of the lowest electricity rates in the country. They also did something really interesting with distance. They called this postage stamp rates, right? You pay the same price to send a letter to New York as you do to your next door neighbor. The BPA decided to do the same thing with electricity, the same low price no matter where you were, as long as you were connected to the dams. So we talked about what was happening out west. You got the Hoover Dam powering Southern California. You have the BPA wiring up the Pacific Northwest. But you talked about the Tennessee River. What was going on over there?
So here we have an experiment unlike anything else. Roosevelt created the Tennessee Valley Authority in 1933 to generate electricity and catalyze manufacturing in the region, but it also provided navigation, flood control, and irrigation to the Tennessee Valley. This wasn't just another power company. This was reimagining what government can do, working across 7 states with one river system to transform one of the poorest regions of the country. The TVA was never just about electricity. It attacked malaria, it built fertilizer plants, it controlled floods, it improved navigation, it modernized the farms.
And why was this such an important region? Well, back in 1933, the per capita income in the region was less than half the national average. This was an impoverished pocket of America. Only 3% of farms had electricity, and the region had been in an economic depression well before the depression that hit the rest of the country.
And if you remember back to Roosevelt's stump speech, he had mentioned this yardstick that he wanted to create. Well, this was it. In the region, private utilities were charging 6 cents per kilowatt hour. And once the TVA was up and running, they were able to sell power at 2 to 3 cents. So this became the yardstick or the proof of what electricity should cost if it didn't have a profit motive. And this gap was the argument for public power.
And the scale was simply staggering. By 1941, TVA was operating 12 dams, producing 2.8 gigawatts of power, using 4 times, they're very proud to emphasize this point, 4 times as much concrete as the Hoover Dam.
And the TVA didn't just sell cheap power and wait for customers to show up. It was actively engineering demand. As we've seen before, we have a marketing campaign to purchase appliances. Let's sell some refrigerators, stoves, water heaters, irons, all available on installment plans, of course, for families who had never owned anything electric.
You could imagine that the private utilities loved all this, no? No, they saw the threat immediately. And so between 1936 and 1939, they filed 38 lawsuits trying to block the constitutionality of the TVA project.
The TVA was massive, and the government was actually executing. And so Roosevelt wanted to replicate the TVA across the country. He wanted regional authorities for Missouri and Arkansas. He was envisioning 10 in all, but every single one was killed in Congress because of the private utility and coal industry. And so this dam building era coming out of the Depression was fundamental to helping us evolve into the mid-century grid that started to become more and more networked rather than a collection of islands.
Exiting the decade, we've electrified the rest of America, and we've brought online these massive, consistent baseload generators in the form of our hydropower across the country. And we're going to need it.
We absolutely are going to need it because in December of 1941, Pearl Harbor changed everything. America enters World War II, and there was a surge in demand for electricity. The war's appetite for power was insatiable.
Building those planes, every B 17 bomber required massive amounts of aluminum. Between 1939 and 44, manufacturing output was tripled. Roosevelt set a goal of 60,000 new planes each year. Aluminum and magnesium production alone required 1/7 of all the electricity used in the country.
3/4 of TVA's power went into the war effort. These cheap kilowatts were smelting aluminum for bombers. They were producing nitrates for munitions. They were critical to our success in World War II.
And there was another new project that was about to draw an immense amount of electricity. The US military needed a special site with special conditions to enrich uranium for the first atomic bomb. And so Oak Ridge, Tennessee was the perfect spot.
The government came in and seized 56,000 acres in rural East Tennessee. They shut down schools and churches and moved communities out. And a secret city of 75,000 people was built from scratch.
And that small 75,000 person city was drawing as much electricity as the entire city of New York.
The TVA was so secretive that even its own chairman didn't know what the electricity was being used for until halfway through 1945.
And the same thing was echoing alongside the other major hydroelectric dams. Back up in the Northwest, the Grand Coulee would power the Boeing factories and also power the enrichment of plutonium for the bomb that was dropped.
And so, because power shortages were thought to be fatal to our national existence, we had to take action on the utility infrastructure. So, the government didn't just ask utilities to cooperate, it ordered them to cooperate. It forced emergency tie lines built between systems that had previously operated isolated islands.
This is actually a really interesting point. When you need more power quickly, you can't necessarily build another dam. But what you can do is connect your grids together to get more capacity. And so the Northwest Power Pool was formed in 1942, aggregating all the hydroelectric resources across the Columbia River Basin. And the Southwest Power Pool was formed that same year to keep power flowing to the aluminum plants in Arkansas. 11 southern utilities were lashed together to form this pool for the same reason.
Right? Since the Insul era, utilities had guarded their territory, but the federal government stepped in and forced the sharing of transmission capacity that they would have never done voluntarily.
And Texas followed the same pattern, but a little bit their own way. They said that they would do it, and so they connected their utilities in 1941 to support the Gulf Coast war production, forming the Texas Interconnected System, later become ERCOT. But they were very careful to keep the boundaries of that system all within the state of Texas.
So it's more like intra-connection than interconnection.
Ah, there you go. So cooperation, yes, but federal jurisdiction for Texas, never.
And the results of all of this cooperation was immediate, right? Between 1940 and 1945, electricity consumption increased 60%, but generation capacity only needed to increase 25%. That gap between consumption and capacity was because interconnection could do load diversity and coordinated dispatch to avoid the build out of new plants.
Insul's insight echoing again and again and again. So connecting systems that could peak at different times and drew on different fuel sources meant the whole system was dramatically more efficient and effective than the sum of its parts.
So as we come out of World War II, we have different pieces of our mid-century grid infrastructure in place. And it's interesting to see how nobody planned it this way, but each chapter of history added another layer. And so we had the advent of electricity and the initial high cost of power leading to bigger plants operating in Insul's natural monopoly. Then comes the Depression and the exposure of the holding company that brought in these state-sized jurisdictions.
Then you had the rural poverty that created the need for cooperatives and brought power to all corners of the nation, followed by the regional underdevelopment that then spawned TVA and Bonneville and brought us the long distance transmission across the country.
And then the war forced interconnection and cooperation to build a connected grid to serve our national interest. This was the essential architecture of the modern grid, forged not by grand design, but by depression and war.
Layer by layer, the modern grid has taken shape, and what emerged was a uniquely American construct. Other countries had looked at fragmented electricity systems after the war and said, let's just go nationalize and centralize the whole thing.
So you have Britain that folded 500 separate utilities into a single state-owned authority to generate all the power on one national grid.
France went even further. They merged 1,700 private producers and distributors into a single government monopoly that is still what dominates the country's sector today.
But America couldn't do that and didn't want to. What we built instead was a patchwork. And every challenge that we're going to see over the coming decades can be traced back to the events and decisions made during these few decades. And so as we exit the war, this new grid is about to get stress tested, not in a time of crisis, but in a time of growth.
And so now we begin the post-war electric boom era. So the war ends and the American soldiers return home and they find their country now sitting on the most powerful industrial machine ever built. We just spent the last 4 years producing half of the world's manufactured goods. And now that massive production capacity was about to pivot towards something entirely different. Let's go transform the American home.
And that capacity was maybe too much for the moment, right? You had massive coal plants and enough capacity for a wartime economy. But in peacetime, our homes weren't really using as much electricity to justify the investments. So the electric industry needed to convince Americans to use more.
You have too much supply, we just need some more demand.
That's right. And so this capacity availability led to yet another massive marketing campaign, not to just sell toasters and light bulbs as we saw in the 20s, but an entirely new vision of how Americans should live.
And this started with the housing product itself. The GI Bill helped 16 million veterans buy homes in these new suburbs. And these weren't just houses, they were blank slates for electrification, built from the ground up with modern wiring, ready for whatever appliances American industry could go and dream up.
And broadly speaking, America was in a pretty good position to be able to do this. We had the capital to invest, we had the factories to produce, and we had the electrical infrastructure to support this new American dream.
And so in 1956, 300 utilities joined forces with 180 electrical appliance manufacturers to launch the Live Better Electrically campaign.
What a thrill to be so free when you live better electrically.
And this wasn't just a marketing campaign, it was a full-on cultural assault. The budget and coordination rivaled propaganda efforts. Their goal was breathtaking in its ambition: make electricity synonymous with the American dream itself.
And who they found for their spokesman was news to me. A one Ronald Reagan. And so for the better part of the 50s, the future president hosted General Electric Theater and gave TV audiences tours of his all-electric Pacific Palisades home. He wasn't just showing off appliances, he was selling a lifestyle. And he visited every GE plant and spoke to hundreds of thousands of employees and became the face of the electric future.
An internal GE memo captured just what exactly their ambitions were. They said, by Thanksgiving, there should not be a man, woman, or child in America who doesn't know you can live better electrically with General Electric appliances and televisions.
And the timing for this was perfect because TV ownership at the start of the 50s was 10%. But by 1960, it was almost 90%. The American population was watching the electric future on an electric device in living rooms transformed by electric light.
And the campaign went one step further, saying, what does the ideal home look like? Well, it's a medallion home that's fully electric. And so by 1970, there were nearly 1 million of these certified medallion homes.
And how'd you earn a gold medallion?
Well, you get a gold medallion if you have an electric washer and dryer, electric waste disposal, refrigerator, and crucially, all electric heating. No gas lines, no oil tanks. Electricity would handle everything at your house.
And just like we saw in the 20s, the marketing campaign targeted housewives with a carefully crafted message: electric appliances to liberate you from the drudgery. ads showing women in pearls effortlessly managing their gleaming kitchens. It was selling time, freedom, the promise of leisure in this newly created suburban America.
And it worked. This didn't just create demand for electricity, it fundamentally reshaped and rewired how Americans thought about modern life. This all electric home became the definition of middle class progress.
The numbers are crazy. The average American home went from using about 1,000 kilowatt hours per year in 1945 to nearly 5,000 in the mid 60s.
That's right. You're going from, maybe a few light bulbs and a radio. And by the mid 60s, you're running a refrigerator, a washing machine, a television, sometimes all at once.
And so, with all this new usage, we know what happens. Capacity gets better utilized, there's greater efficiency, costs start to fall. So, between 1945 and 1965, prices fell nearly 60% in real terms. This is real affordability for the American family.
I feel like if it wasn't so hated, we just call this the insole effect by now. But, like the insole effect kicks in again and the prices keep going down as you get more usage. The utilities solved their overcapacity problem by, of course, creating this new kind of American consumer. The cycle continued. The guaranteed rate of return inside of utilities incentivized them to build, 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 even bigger plants, more ambitious projects, more interconnection. We are inside the age of scale.
And as we know, this wasn't just good for utilities. They had become the largest industry by assets in America, bigger than oil refining and railroads, growing 7% a year, which was twice the national economy.
And so we had the insole effect on consumers, but here it is playing out on the generation side as well, right? Those turbines that he had bet on in early Chicago kept getting bigger and bigger. So we went from 208 megawatt turbines in 1950 to over 1,000 megawatt designs in 1965. Plants became much more efficient in their fuel use, and every percentage point meant millions of dollars saved and millions of tons of coal that didn't need to be burned.
And the business model worked perfectly because prime interest rates were around 3% throughout the 50s. And so if a utility could borrow at 3%, invest that, and earn a regulated guaranteed return of 10 to 12%, the math was irresistible.
And it just created this flywheel. You have to remember, utilities are not a normal business. The key is that they have this guaranteed regional monopoly, no competition, but in exchange, the government decides exactly how much money they get to make, but they do so by investing in new projects.
That's right. So a utility builds plants, they string lines, they maintain their distribution network. This total investment is what you call the rate base. That's what the Public Utility Commission then lets the utilities charge to the customer to cover their costs, in addition to their fixed profits.
As you can imagine, this just incentivizes building the biggest projects you can. The more you deploy, the more money you make.
You have your monopoly, you set your prices, you get a guaranteed return, and American society gets reliable service.
The incentives were perfectly aligned. Utilities wanted to build bigger because it meant more profit. Consumers benefited because bigger meant cheaper. They had more things to plug in. Cheaper power is great. And regulators looked like geniuses. Everyone was winning.
So you've got these new homes being built and newly electrified appliances. And World War II had massively expanded our generation capacity. But let's take a look at what's driving all of this. Now, for those of you that have spent some time with us, you'll know from the coal episodes that it had become America's workhorse fuel since the 1800s. But by 1920, it had become more like a one-trick pony because 90% of it was used for railroads and less than 10% of coal was being used to power factories and homes sitting on this new grid.
And so a sort of major displacement was taking place. Oil had conquered transportation. Natural gas pipelines started to snake across the country, stealing the home heating market. Coal needed to find its consistent partner, and it found salvation in the one industry that was booming, electric power.
And coal was perfect for running around the clock and providing baseload power to complement the hydro that was needed during wartime and after. And coal-fired plants grew to provide about 70% of American electricity by 1935. So coal hadn't just found a customer. Coal had found its lifelong destiny partner in the grid.
And as we said, this industry is booming 7% a year, building bigger plants every year, incentivized to build the next bigger and bigger plant, actively rewarded for the most capital-intensive projects. And coal plants were exactly that: massive boilers, elaborate coal handling equipment, enormous cooling systems, eventually large scrubbers.
And the fuel itself was cheap, right? Coal is cheaper than gas, it's cheaper than oil. So utilities are running it around the clock, spreading those high capital costs across as many kilowatt hours as possible. The more hours you run, The cheaper your kilowatt hour became, the more efficiently you could drive power out of each rock.
And so this black rock that had powered the first industrial revolution in the forefront had now found its massive second act, but it was now invisible, hidden behind the power plant walls. So we have this booming grid across America. We've got these massive hydro sources that we built during the New Deal era. We have these expanding coal plants, but now we got to increasingly move this large amount of power around the country. And so between 1950 and 1963, American utilities built 80,000 miles of transmission lines. That's enough to wrap around the earth 3 times.
If you remember back to the AC/DC wars, we want to move electrons efficiently across long distances to be able to separate generation and consumption.
And the electricity coming out of a power plant starts at a relatively low voltage, maybe 20,000 volts coming out of a generator. That's enough to power the neighborhood next door, but it can't travel far at that voltage.
Right. And you push electricity through that wire and it meets resistance. The longer the wire, the more energy you stand to lose. So if you try and push that 20,000 volts across a couple hundred miles, you'll lose that energy before it arrives. Think of voltage like water pressure. You need enough of it to move across a long distance.
The magic of AC is that it can be transformed without energy losses. The power coming out of Hoover Dam is maybe at 16,500 volts. We step it up to over 200,000 volts, transfer it across to LA to a Nye's house. At a substation, gets stepped down to 12,000 volts to the pole at 240 volts, and now at 120 volts out of his outlet into his laptop where we're recording this. That chain from generator to transformer to high transmission line to step down is the core anatomy of the grid.
And remember, the system ended at the utilities boundaries. There weren't wires necessarily connecting them until we forced greater and greater interconnection. So these wartime power pools prove that connecting isolated systems was hugely valuable. And now in peacetime, in the build out of the 50s and 60s, we began building those permanent links to our electrical islands. So now every major utility was interconnected with its neighbors.
And of course, as time went on, the higher the voltage, the lower the losses, and we'd keep growing those distances. By the early 50s, a utility fired up the first 345 kilovolt line. Within 20 more years, we doubled again, pushing 800 kilovolts. And so by the mid 60s, we ended up with 3 core distinct grids in the US that we still have to this day. We have the Eastern Interconnect, which reaches from central Canada eastward to the Atlantic coast, all the way south to Florida, and back to the Western Great Plains. We have the Western Interconnect that goes from Western Canada all the way down to Baja California and Mexico. And then we have Texas continuing to do its own thing. Now let's talk about what happens inside each of those grids.
If you think this system of moving power across long distances is magic, well, this is where engineers get even more goosebumps. See, linking separate utility systems into a single synchronized network isn't just about running a wire between 2 neighbors. It's actually forcing every generator on the connected network to spin in perfect lockstep.
I got goosebumps. Let's go. So right now, all of the hydro plants in America have these massive steel rotors. All of the coal gas stations have these massive spinning rotors the size of school buses that are spinning at exactly 60 hertz, 60 times a second, or 3,600 times a minute. Not 3,602, exactly 3,600 times a minute. And that precision, that relentless mechanical perfection, is why electricity is coming out of your wall at exactly 60 hertz.
All of them synchronized perfectly in revolutions per second.
Every AC generator in a given interconnect is moving together. What I'm saying is that the spinning bus in the Hoover Dam and the spinning bus at the Grand Coulee are spinning not just at the same speed, but actually physically locked together as they spin like a synchronized swimmer.
And so when new load comes in, these massive spinning school buses feel it instantly and start to slow down. And operators of the grid have to open more valves, let in more steam or water, push them harder to maintain that exact 3,600 revolutions per minute.
And when you say feel, we mean that there's this electromagnetic force. It's like a brake being applied to a spinning wheel. They feel the resistance of that light switch being turned on.
And how do we manage all of this? Well, the grid has these automatic systems called governors, which basically are cruise control for the entire continental power system. They detect these tiny frequency changes and adjust the input of fuel within milliseconds. Because if the frequency drops from 60 hertz to even 59.7 hertz, there's a response.
And so all these spinning turbines that are synchronized together as one machine creates a very real physical inertia that keeps the frequency stable across the entire grid. And so the bigger the machine, the more spinning weight added to it, the more stable the frequency of the grid.
And this is happening right now on this recording between Seattle and LA, synchronized into a single interconnect.
Our electricity is moving together.
These synchronized spinning school buses is quite literally why we call the grid the largest machine ever built by human beings, because it is operating literally as one single machine.
So, in addition to the physical inertia that gives you that frequency stability, why else are these hyper-connected massive grids so valuable?
It gives us incredible reliability, right? You have different regions peaking at different times, using different fuel mixes and facing different weather conditions. You need the interconnected grid to be the sum greater than its individual parts.
And then, in addition to that, you then get the economic benefits of being able to use cheaper generation across a larger grid at any given time.
And so, this sharing of electricity and sharing of diversity is what makes the grid function almost 24/7, 365. And the amazing thing about it was it wasn't planned top down. There's no blueprint for a continental scale synchronized machine. It emerged through thousands of individual utilities forced to connect to their neighbors, build transmission lines one at a time until the whole thing has become virtually inseparable. And that's why we kind of say that the grid was created rather than we created it, because it happened partly on accident.
By 1970, America had achieved something unprecedented. In 1920, only the poor and rural had no access to electricity. By 1970, only suspect radicals and known freaks were now off the grid. To be American was to be plugged into the grid.
And the usage proves that out. The average American used 25 times more power in 1970 than they did in 1920, driven by nearly 80 years of declining costs. This was the natural order of things.
Every major appliance reached near universal adoption. The grid had grown from isolated urban islands to this continental scale network, and the US was dominating electric production. We are at the ending chapter of the golden age of electricity, and boy, did it deliver.
4 decades of epic growth and transformation. So, what could go wrong? Certainly not 4 decades of complexity, conflict, and decline.
Now we're about to witness some of the complexities of that interconnected grid. We call this era the cracks of scale. So it's November 9th, 1965, and a single relay trips at the Niagara Falls power station. This is a protective device that was set years earlier when power flows were much lower. It triggers. It was put in place to prevent an overload. Instead, it kicks off a cascade.
And so power surges to other lines. They start to overload. Those governors trip. They disconnect. More surges, more disconnections. Within 5 minutes, the entire Northeast grid is tearing itself apart, breaking itself back up into these isolated islands as station after station automatically shuts down, following its secure protocol.
Within 12 minutes, 30 million people are plunged into darkness across 8 states and Ontario. 800,000 riders are trapped in New York subways. Office workers are stuck in elevators. The greatest engineering achievement in human history has just revealed a fatal flaw.
That's right. On this November night, we discovered what it meant to be a system of systems, bolt-on technologies that just happened to work. And these interconnections that had made the grid so strong had also made it quite fragile. One relay, 30 million people.
This blackout shocked the industry awake. Within months, 12 large power pools formed NERC, or the National Electric Reliability Council, to set the first reliability standards. It was the industry's attempt at self-regulation, a preemptive strike to stop potential federal control.
The grid had been built for eternal growth. More plants, bigger lines, endless expansion. This blackout was the first big crack of that certainty. And the lesson was clear. Underinvestment in any part of the grid could cascade to all others.
These many interconnections each made an individual utility more reliable. And if your plant tripped, you could draw power from your neighbor. But the same system created a system-level vulnerability that hadn't existed when utilities were their own islands. Failure in one system could now propagate through all the interconnections in the system that were otherwise healthy. The very feature that made the grid so much more reliable in normal times also made it more fragile in an abnormal outage. And so this major 1965 outage was the first crack on the benefits of scale and interconnectedness. But we started hitting up against some new cracks of scale at the station itself. For 80 years, we'd followed one simple formula. You build the plant bigger, you get the steam hotter and higher pressure, and it worked. Edison Station managed just 5% efficiency. By the 1920s, we'd hit 20% efficiency. By the 40s, 30% efficiency. All of a sudden, though, we started to hit a plateau.
Engineers keep building hotter and push steam past 1,000 degrees to the point where they started to see turbine blades deform. So bigger and hotter was suddenly no longer better, right? These larger plants had larger cooling systems, more pollution controls, larger everything. So the cruel irony of this economies of scale that had driven all of the cost declines was hitting a diseconomies of scale. And to make matters worse, talent had evaporated from this industry. Aerospace and defense were attracting all the great engineers. So for the first time since Edison, the cost curve was about to bend the wrong way because we had hit our limits of physics, innovation, and creativity.
So while we're hitting the limits inside of coal plants, there's another new way to heat up water and spin those steam turbines. Let's go back to 1953. You have President Eisenhower standing before the UN making a promise to develop peaceful atomic power. He said, "Peaceful power from atomic energy is no dream of the future, that America will strip the military casing from atomic energy and adapt it for peaceful purposes." It was called Atoms for Peace, and it was going to change everything for the electricity sector.
And the industry believed it and jumped on. Between the mid-60s and the mid-70s, the utilities went on a nuclear shopping spree, ordering over 200 reactors. Almost every operating reactor in America today got its construction license in this narrow window. It was supposed to be the next great leap, the technology that would make coal obsolete.
And it wasn't just that nuclear was exciting, but the fuel supply for conventional plants was starting to become unreliable, right? A lot of the easily accessible oil had been drilled. The exploration for new oil had turned increasingly more costly and environmentally damaging. Natural gas prices were also starting to increase. And so by the late 1960s, gas shortages were starting to emerge as well.
So you had fuel price pressures. You also had industry forecasts of 7% annual growth continuing. What that means is electricity demand was projected to double every 10 years. This is the backdrop by which you're ordering multi-billion-dollar nuclear plants, right? Every investment decision, every plant ordered, every transmission line designed is premised on this doubling of electricity demand. And so when utilities would begin construction of a plant, it wouldn't come on for 8 or 10 years. And they were confident that that demand was going to be there to meet the capacity.
But nuclear was different than other plants. It wasn't just a bigger coal plant. These were staggeringly new and complex machines that pushed American manufacturing and engineering to its limits. Every component had to be perfect. Every weld had to be flawless. And the precision required was unlike anything the power industry had dealt with in modern times.
As the plants got more complex, the construction schedules stretched. 5, stretched to 10, stretched to 15 years. And this was all being financed on debt. And so the interest rates started crushing them. Utilities had bet their future on nuclear and found themselves drowning in debt that they would ultimately try and pass to ratepayers. And remember, this is all under the backdrop of the regulated utilities' guaranteed rate of return. So nuclear was even more attractive in the 60s because it was higher capex than coal. Bigger investments, bigger returns, sometimes even if they didn't turn on.
In fact, it was said that the Southern Company and other nuclear utility builders made more money by going over budget than they had by turning the plants on. Ultimately, ratepayers were left holding the bag, even without getting cheaper electricity prices. Between 1971 and 78, the cost of building a coal plant had increased nearly 70% in real terms. Terrible for the scale of that industry. Nuclear during that same time, the cost increased 140%. This technology that was supposed to save the industry from coal's limits of scale had become an even more expensive trend.
And why do we say supposed to save? Well, it's because of the 253 nuclear plants ordered during this boom time, almost half of them were canceled. No nuclear plant ordered after this period was ever really completed. They had to write off billions of dollars.
And the event that kind of sealed the door shut from further improvements was 1979, the 3 Mile Island incident. This was the worst accident in US commercial nuclear power history. It crystallized a societal fear, and no more licenses were issued.
And we'll explain in just a moment why these plants were canceled. But it's important to just keep in context that nuclear failure was different from normal business failures. A normal company would have been destroyed, but utilities weren't normal companies. They passed these costs straight through to the ratepayers. So electricity prices kept climbing, in part because the customers were paying for power plants, which would never generate a single kilowatt.
But with all of this, we sound maybe a bit over negative on the impact that nuclear has had on the US grid. The plants that did get built, they have become some of the most reliable power generators America has ever operated. And they, in particular, have an amazing high capacity factor. That's how often they're actually running and generating power. So by the 2000s, their capacity factor was over 90%, higher than coal, higher than gas, higher than any other source on the grid. So these nuclear plants that we've had up and running have provided decades of steady, carbon free baseload power. So the technology worked. It was really the deployment model ultimately that was broken. But why did so many nuclear projects never ultimately come to fruition?
One underlying movement that was brewing at this time that contributed to the slow permitting and ultimate regulation of this industry was growing environmental awareness in the American public.
That's right. You go back to Pittsburgh in the 60s, and drivers in the middle of the day had to use their windshield wipers, not for rain, but to clear away the soot so that they could see the road. Power plant emissions were killing crops, poisoning rivers, and distributing acid rain over the lands. And so this is the era where you have Rachel Carson publishing the famous Silent Spring. Something began to shift in the public's consciousness. And on April 22nd, 1970, we had the first Earth Day. And 10% of the country, 20 million people, took to the streets to march for the environment. It was the largest demonstration in American history.
And then came the political response, fast and bipartisan. One Richard Nixon stood before Congress and said, "Shall we surrender to our surroundings, or shall we make peace with nature and begin to make reparations for the damage we have done to our air, our land, and our water?" Nixon signed the National Environmental Policy Act, the Clean Air Act, and created federal agencies that had real teeth to tell power plants exactly what emissions to control and what technology to use.
And as you can imagine, this is a massive shift for utilities, right? Coal plants had been turning out cheap power, and now they needed all of a sudden all this new equipment, cooling towers, scrubbers, millions of dollars in equipment that did nothing to generate electricity. But, capital costs exploded, worked okay for their business.
Yeah. And the results of this from an environmental perspective actually bore fruit. Over the next 50 years, emissions of the six most common pollutants dropped about 80%. So while the economy tripled in size, the air actually got cleaner.
And so this was really the end of an era for the power industry. Every new regulation added costs and delays. Every environmental review slowed down the building of the next plant. And so the model that had built the grid and this American prosperous engine of burn cheap fuel, ignore the externalities was now gone.
And the environmental moment was a critical factor in changing the power industries. There was also economics and geopolitics at play at this time.
So we entered the 60s with the 65 outage. We had the plateau of gains from the larger coal plants. And now we have this environmental awareness that's starting to pump the brakes on this build, build, build mentality.
We're not done yet. Throughout the 50s and 60s, oil was actually cheap and clean burning compared to coal. It was easier to handle without the coal trains and ash. And so you had utilities across the country spending billions of dollars to convert coal plants to burn oil instead. And this was accelerated by these new air quality regulations. And so what happens over the course of 2 decades is you go from zero electricity production fueled by oil and gas to about a quarter in the late 60s.
This oil at the time was coming from the American oil fields that had just been pumping flat out since the end of World War II. And in 1970, that production peaked, something we can only understand now in hindsight. And so we started to fill that gap with large amounts of imports for the first time. And so imports doubled from 70 to 73, rising to 36% of total US consumption, connecting us further with the global oil markets.
And then, October 1973, Egypt and Syria attack Israel, launching the Yom Kippur War. Utilities had just spent a decade switching to oil, found themselves dangerously exposed to the oil markets. And Arab members of OPEC announced an embargo in retaliation for Western support of Israel. Oil prices jumped 70% almost overnight.
By the time the embargo ended in March of 74, oil prices had quadrupled For Americans who had never imagined scarcity filling up their gas tank or using electricity, gas lines stretched for blocks. The speed limit was dropped to 55 miles per hour just to save fuel.
And to make matters worse, the old rate structures were actively rewarding waste. Utilities had these declining block rates, so the more electricity you use, the cheaper each additional kilowatt hour became. A factory that actually left the lights on burning all night paid less per unit than a household trying to conserve, which all made sense when plants needed high utilization and fuel was cheap, but ceased to make sense in a moment where prices were through the roof.
That's right. So now we have oil prices soaring, new plants costing billions. The entire pricing model was backwards. Insol's there turning in his grave. And so in February 77, President Carter appears on television in front of his fireplace wearing his cardigan sweater and urging Americans to please turn down their thermostats and put on a sweater. He's got his soft Georgia accent, and he says, "We must face the fact that the energy shortage is permanent. There is no way we can solve it quickly."
The economy entered a huge recession. It was essentially the slamming of the door on this post World War II economic growth miracle. You had unemployment hitting 10%, inflation going from 3% to over 14%. The economy was thrown into upheaval.
And this crisis was elongated when in 1979, the Iranian Shah was overthrown and the instability came for Iran's massive oil supply. And so we just had this period that stretched on from months to years to the decade of economic energy crisis.
And so for the utilities, this was a perfect storm, right? They had been in a motion of build, build, build. They'd financed all of these large infrastructure projects with assumptions of demand and low rates. And now you have fuel costs going through the roof, construction projects delayed, interest rates going from 7% to north of 21%, making construction untenable and the entire business model in question.
That's it. I mean, they were trapped. They couldn't stop building a project mid-flight, but they also couldn't afford to keep building with these interest rates skyrocketing. And then even if they finished, the customers weren't going to be happy with ultimately the new costs on their bill.
Yeah. Who's left holding the bag? It's the consumer, right? On the one hand, they're facing skyrocketing costs getting passed to them. They're facing uncertainty around the reliability of infrastructure. And they're starting to listen to Carter. Conservation becomes a culture. People are turning down their thermostats. They're installing insulation. They're buying smaller cars. Carpooling becomes a patriotic duty. They're sacrificing their own convenience because the model was finally breaking.
And suddenly, the utilities need to print conservation booklets and create departments dedicated to reducing demand. Growth was no longer the operating word. For 80 years, the electricity business had just one commandment from Samuel Insull: grow. Through the 1960s, success meant building bigger plants, serving more customers, selling more kilowatt hours. The whole financial model depended on it. A power plant only pays off when it's run at near maximum capacity around the clock.
And this wasn't just about the prices. It was also about trust and reliability in a system that was providing for everything that was fueling the economy. But when bills came due on all that nuclear build-out, the rate commissions that had approved the investments from a decade earlier now called them imprudent and refused to let the utilities recover all of that cost. This regulatory compact, guaranteeing return on prudent investment, was also starting to fall apart.
If Carter asked the American public to conserve, who was its intellectual prophet? Amory Lovins, a physicist who coined the phrase that would still haunt utility executives for decades. He said the cheapest kilowatt hour is the one that you never had to generate.
Such a simple sentence that drove an entire philosophy, right? So in 1976, he comes out with a very prescient framework around the future of energy systems. On the one hand, you can have the hard path, which is what we've been following for decades. Build bigger coal plants and nuclear plants, centralize generation, build longer transmission lines, have supply meet the demand no matter what the cost.
On the other hand, we could build the soft path. This is efficiency first, then match smaller decentralized sources more locally to match what you need in those moments, and ideally build those with new sources like solar, wind, cogeneration, and storage. It combines a prompt and serious commitment to the efficient use of energy with the rapid development of smaller scale decentralized sources.
And asking the utilities to adapt and promote conservation was like asking a tobacco company to discourage smoking, right? Their entire existence depended on kilowatt hour sales. So conservation was a threat to their bottom line.
But it stopped being hypothetical. By the late 70s, electricity demand growth had slowed from 7% annually to near zero.
In addition to that, for the first time ever, we saw prices getting more expensive. Residential electricity prices from 1970 to 1985 more than tripled, and industrial users had it even worse with their prices quadrupling. So this is aluminum smelters and paper mills that were located near very cheap power suddenly not being able to compete and shutting down.
Bigger was no longer better. Environmentalists wanted cleaner power, and a new breed of economists started asking new and dangerous questions. What if electricity didn't need to be a monopoly after all? Carter understood that these piecemeal reforms wouldn't fix what was fundamentally broken.
And so in 1978, he signed 5 major energy bills, the most sweeping intervention in the energy markets since the New Deal. This creates the Department of Energy, it establishes the Strategic Petroleum Reserves, and forces utilities to provide conservation services to their customers.
Most dramatically, he banned the use of oil and gas, shifting everyone back to coal and nuclear, which were becoming two of the most expensive fuel sources. This ban wouldn't be removed until a decade later in 1987, and that would unleash the natural gas industry going forward.
So Carter passes this sprawling Energy Act, and buried deep inside was a little-known Section 210 of the Public Utility Regulatory Policies Act, PURPA.
And so with that little clause, we enter what we're calling the era of restructuring, a couple decades of the industry trying to pull apart what Insull had bolted together.
This section of PURPA was in there because a Senator Durkin from New Hampshire had wanted to help a garbage burning plant in his district sell electricity to Boston, right? So they were burning trash. He wanted to capture that heat and sell it back to the grid. The utilities barely noticed. They had bigger problems on their hands than some senator's pet project.
But it said something that sounded pretty simple. Utilities would have to buy electricity from any qualified facility that was producing less than 80 megawatts. And they'd have to pay what's called avoided costs, which is whatever it would have cost them to generate that power themselves. What nobody realized when this law was passed is that this minor little subclause in a section for the trash-burning cogen plant had just broken the utility's total control over the generating power of our electricity system.
Because utilities aren't just monopolies. They're what's called monopsonies. They were the only sellers and the only buyers of electricity in their territory. So if you had a factory that could generate power, tough luck. The utility didn't have to buy it. This little clause within PURPA changed that overnight.
And cogeneration wasn't a new thing. Back in 1912, industrial cogeneration plants, which are factories that captured waste heat to make electricity, had produced more power back then than utilities. But by 1962, utilities had squeezed them down to less than 10% of generation that was used. After PURPA, they came roaring back.
And utilities had a problem on their hands that they never imagined. See, they'd always controlled exactly how much power flowed where and when. Now, electricity could come streaming into their lines from anywhere, and they just had to pay for it and figure out what to do with it.
And they didn't know how much to pay for it, right? Because this avoided cost calculation became a complex nightmare. After 50 years without competition, utilities didn't actually know how much it cost them to generate a kilowatt hour. They just did it and passed on their total costs to ratepayers. Now they needed to know. The joke was that PURPA should be called the Full Employment Act for Economists.
And states everywhere are now scrambling to implement this. So New York's like, well, let's do 6 cents a kilowatt hour for everyone. And Virginia's like, well, let's try competitive bidding. When they asked for 1,000 kilowatts of generation, they got bids for 5,000 kilowatts from 53 different companies.
And so our cardigan-wearing, soft-spoken president who had asked Americans to turn down their thermostats had somewhat unwittingly unleashed market forces that would transform the electricity markets into one of the most volatile, competitive businesses in America. The age of growth and stability had ended, and the age of markets was about to begin.
And up until this point in the story, we've talked about how Texas is special, but it makes me feel like we're shortchanging California, my home state. So let's talk a little bit about how California is special, for better or for worse, as we go forward. We didn't just implement PURPA, we supercharged that puppy. We required utilities to buy power from independent generators at fixed prices based on the forecast that gas and oil would keep getting more expensive, locking in high escalating rates for years into the future.
And so the response was explosive. In 1981, California had just 10 megawatts of grid-connected wind power. By 85, just 4 years later, it had 10x, built entirely by independent producers that were chasing PURPA-enabled contracts.
Our California became the center of the renewable universe. By 1990, the state housed 85% of the world's wind electricity capacity and 95% of the world's solar capacity. The Altamont Pass sprouted thousands of turbines. Palm Springs became a forest of spinning blades.
This happens to be where a little over 11 years ago I proposed to Anna. As a
Was
beautiful
it near
backdrop.
one of the wind turbines?
It was, yeah. They're in the background.
There you go. Thank you, PURPA.
Thank you.
And something else was happening too. You had these complex tax credits and guaranteed contracts that were entirely new. Renewable energy was now a financial product. And what follows is an oil price crash in the mid-'80s, and the California renewable bubble pops. Those generous avoided cost contracts made sense when your competing fuel was extremely expensive. But when your fuel prices drop, you have utilities like PG&E locked in to paying a higher cost of energy than they could recoup.
It's the folly of ever presuming that your low prices will always stay low for energy or that your high prices will always stay high, right? And so the regulator, CPUC, got spooked. They had 8 times the demand that they had forecast, and so they paused the program. PG&E had signed these contracts locking in that they were going to pay 10 cents per kilowatt hour for wind energy when the rest of the market wholesale prices had dropped to 3 cents. And so they were hemorrhaging money on that spread and forced to keep paying those expensive contracts out while they had cheaper gas plants that were sitting idle.
So PURPA had done something irreversible. It had proven that non-utility generators could produce power at scale, that you didn't need to be a giant vertically integrated monopoly just to build a plant and put power on the grid. Now, the prices were still a mess, but the principle had been established, and once that door opened, there was no closing it.
And this is the beginning, not the end of the opening of electricity markets. And here's the problem with trying to create an electricity market. Electricity is not like any other commodity. You can't store it in a warehouse when prices are low, ship it in a container to where prices are high. It exists for a fraction of a second, created and consumed in that instant.
And as all of us now physics experts know, when you flip a switch, somewhere a generator has to produce exactly that amount of power at exactly that moment. Can't be too little, can't be too much. And it's really hard to create a market in such a fragmented ecosystem. You had 3,300 utility companies, but 2/3 of customers paid their bill to just about 200 giant ones, and the rest were these tiny municipal operations.
But the grid, when you zoom out, is this patchwork of little fiefdoms. Each utility is king of their own domain, and all interconnected but jealously guarding their borders.
And so this system that was transforming into a market was a first major step. Now, where did this idea come from? Well, the intellectual ammunition for this came from, no surprise, the University of Chicago, a 1971 academic paper by economist George Stigler. So what Stigler argued was that regulated industries didn't just tolerate their regulators, they actually captured them. Regulators didn't tame monopolies, they became their servants. And for this, Stigler won the Nobel Prize.
And so Jimmy Carter, in 1978, the same year that PURPA passed, he signed the Airline Deregulation Act, kicking off a wave of these sorts of acts to deregulate what had previously been these centralized industries. And the effects of this were immediate and intoxicating. Carriers all of a sudden could fly wherever and whenever they wanted and charge people whatever the market could bear. And very quickly, you saw these startup airline carriers that were charging crazy low prices to open up new routes.
Carter liked this deregulation thing, and he kept on rolling. He opened up trucking and railroads. Within a decade, freight rates had fallen dramatically, and the industry actually turned profitable again. And then comes Reagan to pour gas on the fire that was already burning.
And then we have the big one, 1984, the breakup of AT&T, Ma Bell. AT&T had controlled the American telecommunications industry since the 1870s, and it was split into 7 regional companies. It showed that you could take one vertically integrated monopoly, smash it into pieces, and the system could still work.
And by the late 80s, the deregulation template was set, and it was extended to financial services, natural gas production, natural gas pipelines. In fact, FERC issued an order requiring interstate gas pipelines to open up access to any shipper that wanted to use them. So if you had gas to move, the pipeline had to carry it, which would become the template for what FERC did for electricity along transmission lines.
And so the question everyone was asking themselves is, why can't we just do the same thing with electricity? Sure, we've been treating it as a natural monopoly, but we'd also treated airlines and trucking and the telephone system the same way. If those work to split up, as quote unquote natural monopolies, why is generating power any different?
The most radical experiment of this played out 7,000 miles away. Down on the western coast of South America in 1970, Salvador Allende wins the presidency of Chile. He immediately nationalizes more than 500 companies, including the entire electricity system. He then freezes prices while printing money, and inflation spirals.
3 years later, the military launches a coup to stop this madness. General Pinochet seizes power, and to fix the economic ruins, he turns to an unusual group, a team of young Chilean economists that were trained under Milton Friedman, known as the Chicago Boys. And their diagnosis was, of course, simple. All we got to do is get the government out of the way.
Generation, transmission, distribution, split it all apart and privatize it. Create a wholesale market where generators compete. The cheapest plants are dispatched first.
Private investment pours in, capacity triples, and the World Bank holds up this model and starts to bring it to other countries around the world.
Classic World Bank move. In the late 1980s, Margaret Thatcher was ready to apply the same logic to one of the world's most successful state-owned electricity systems in the world.
Thatcher didn't privatize because the system wasn't exactly working. She had deep political motives for changing what was happening.
For example, she wanted to finish off the coal miners, whom she had been battling for many years.
And so you had declining prices there as well, which everyone held up as this great story. But what few people look back understood at the time was that this was really spending down the infrastructure investment that was made in the centralized era in the UK, and that would eventually come home to roost. All people could see was the falling prices.
So now it was America's turn to step up to the plate. And in 1992, they did something that would have probably horrified Samuel Insull. They officially divorced electricity generation from transmission. The Energy Policy Act declared that power plants and power lines could be disconnected, which let non-utility companies build power plants and sell electricity at wholesale. It also gave FERC the authority to order open access to the transmission lines. If you had power, you could now use those lines.
And FERC further gave states options to push the divestiture of assets. And so California, Texas, and parts of the Northeast either required or encouraged utilities to sell off many of their generating assets. Utilities that had controlled every aspect from generation to transmission to the consumer's light bulb on the other side were now pushed to offer transmission access to competitors on the same terms they gave themselves, a non-discrimination principle. From now on, many utilities would become primarily pipes and wires companies. They'd make money by moving electricity, not producing it.
And so for the first time in history, electricity prices would be set by traders sitting at desks trying to anticipate the demand in one city at the time of day, day of week. They'd buy the cheapest power they could find on the market, and they'd sell it off for a profit.
Kilowatt hours had become tradable commodities. And the grid started groaning under this new strain because there's now an economic incentive to try and move power and generate power further and further from where maybe it should logically be generated because you want to make money on the available spread. Before this order was passed, the East Coast averaged something like 10 transmission overload warnings per month. 6 months later, that jumped to 175. And by 2003, it hit 250 overload messages a month, 25 times what it was doing before.
This system wasn't designed for this. Wires built for local reliability weren't equipped to do long-distance wheeling. It's like having a neighborhood street handle interstate truck traffic, right? You have the infrastructure built for the purpose of keeping the lights on locally, now being used to make money by moving power across state lines where it was most profitable.
And I think what we are quickly rediscovering is that America's grid is vastly more complex than what we had seen happen in Britain or Chile. We had thousands of utilities, 50 state regulators, massive distances, and diversity across the country. If we were going to have struggles in rolling out a restructuring of the industry, it was going to happen here.
Now, this is often called the deregulation era or the deregulation of the energy sector, but that's not quite what it was. It was actually a regulatory shift. We actually got more, not fewer rules at every step of the way. And it was the new rules and institutions that were replacing old ones. So we had to create wholesale markets. We had to create these capacity and ancillary markets, which we'll talk about. We had to create a new regulatory apparatus. We'd prefer to call this the era of restructuring.
And in this restructuring, the fundamental business models of electricity started to get turned upside down, right? Utilities used to just make more money when people used more power. Now they made money by moving power around. The physical grid itself, actual wires and transformers, became an afterthought compared to the financial products that were going to be built on top.
And so Washington had declared the grid to be a marketplace. And now we need the regulatory structure to start to evolve and follow along as best it could under this new situation.
And so, to make this new electricity market work, someone had to be the referee and set up the guardrails. Enter the concept of RTOs, or Regional Transmission Organizations. Before deregulation, each utility managed its own system. Now you needed someone neutral to coordinate the whole circus.
And this model isn't entirely new. Power companies have been coordinating since the 20s when Pennsylvania and New Jersey actually created the PJM interconnection to share reserves and balance loads. But it wasn't until 1999 that FERC asked these old power pools to transform into something very different: independent operators actually running markets.
And remember, you're creating this market for this thing that has to be consumed and generated in real time. And so every generator needs a way to bid in. And if supply and demand aren't matching perfectly, the whole grid can collapse.
So the RTO was attempting to be that solution. They don't own the power plants, they don't own the transmission lines, they just run the markets. So now instead of creating bilateral relationships every time you wanted to move electricity, you now had this overarching organization that was managing the flow in a market system. And these new organizations covered large swaths of the country. So PJM, which I mentioned, expanded from Pennsylvania and New Jersey to include Maryland, Delaware, Virginia, and more. Then you have the Midwest Independent System Operator,
MISO.
which was coordinating 15 states from Montana to Michigan. You have New England and New York getting their own ISOs, California creating CAISO. All of this to manage these newly deregulated systems, acting as the operators of these markets.
And Texas, always a special Texas, went its own way. ERCOT evolved from a 1970s reliability council into the full market operator in 2002. And they continued to make sure that they kept their grid entirely within state borders so that they would not have FERC oversight. Texas could design its own market rules then while thumbing its nose at the Washington overseers.
And the geography of these territories split America in two. You had about 2/3 of Americans living in RTO territories where power plants competed in wholesale markets and prices fluctuated with supply and demand. The other third, mainly the Southeast, Mountain West, and Pacific Northwest of this country, stayed in the old model of vertically integrated monopolies. And interestingly enough, these geographic areas are also where there are large hydro sources powering their grids.
So we had our basic market design that we just talked about, but within one of these RTOs, what is actually going on? What do we mean as a market? Well, really, there's three markets. There's one for buying and selling energy. There's one for encouraging excess capacity to be available. And then there's one called ancillary services to stabilize generators and ensure that we have that sweet, perfect 60 hertz always in sync.
So for the purposes of buying energy, first you've got the day-ahead market. Generators submit their offers for each hour of tomorrow based on their forecast. And then the algorithm solves for the cheapest generation schedule that won't overload the transmission lines. Now, the reality is that it never matches plan, right? A generator will trip offline, temperatures will spike, someone will increase load unexpectedly. And so you have a secondary market called the real-time markets that are running continuously, almost every 5 minutes, to redispatch generators and keep supply and demand in perfect balance.
And as RTOs formed, there was fierce debate over how exactly we should do pricing. And most ultimately settled on what's called locational marginal pricing. Really, what this means is just different prices at different points in the grid to reflect the costs and congestion of transmission. Think of it like Uber surge pricing, but for electricity.
And then come the capacity markets that Ben mentioned, which is very particular to energy. So in a normal market, when demand is high, prices rise and supply follows to the highest paying customer. But in an electricity market, when demand is high, you want to cap prices to prevent the public from spending too much money. So a capacity market is something we invented to actually pay generators to simply be available for periods of unexpectedly high demand. So they're paid to keep capacity available.
And so you think about the cycle time of this, right? Capacity is about building new plants. This is a market that exists on 1 to 5 year time horizons. You have the daily and minute based energy markets. But there's one more market that you need, which is controlling that crucial frequency of the grid. So the ancillary markets are all about frequency regulation, and it requires that generators can respond to signals every 2 to 4 seconds, ramping up or down to keep the grid exactly at that 60 hertz. These are spinning reserves that can provide backup and increase their output within 10 minutes if another unit fails.
So, as you can tell, these are very complex systems that were designed not just to be markets, but to obey the laws of physics, because the alternative is a blackout. And so we had to create these complex structures. And instead of the government completely extricating itself from the electricity business, it was required to create new levels of oversight to ensure that we had the proper backstops on this national infrastructure.
So now that we've gone through our Power Markets 101, let's go back to California. In 96, California's system was a mess of expensive mistakes. Retail rates were some of the highest in the nation. They had those overpriced wind contracts from PURPA that we had just talked about a bit earlier. And they had a number of costly nuclear plants that ratepayers were now paying back. And so when politicians looked at the idea of restructuring, they were excited. They thought, just like we had with the airlines and telecom, this is an opportunity to bring in competition and lower prices. It was politically way too good to resist. And so they introduced a bill that included a guaranteed 10% reduction of retail rates for small customers as a little sweetener to make sure that politically everyone was on board. And the bill accomplished this by capping retail rates. Shouldn't be much of a problem given all this new competition that's going to come in, right?
This capping of retail rates was an unmitigated disaster. They basically deregulated wholesale prices while freezing the retail rates at 6.7 cents per kilowatt hour. So the whole pitch was that competition would bring down prices. And so if you froze the rates, it was acting more like consumer protection rather than a ceiling. But that doesn't actually work because utilities were then forced to buy power at whatever the market price was and sell it at or below this fixed price.
But the political salience was so strong. The state law passed unanimously. PG&E, SoCal Edison, San Diego Gas Electric, they sold off all their fossil fuel plants to merchant generators. They transformed their companies that had made and delivered power into companies that were just there to deliver it. And they had to go buy whatever was delivered on the open market by this new realm of generating companies. In fact, they were so behind it, the bill was largely drafted by the utilities, I think even at SoCal Edison's offices.
Amazing. To compound all of this, you had a massive capacity issue facing California. So the dot-com boom pushes electricity demand through the roof. And at the same time, a drought in the Pacific Northwest reduces hydropower imports. All of this while California was retiring much of its backup generation. And so the companies that bought the utilities' old plants realized they held a massive amount of market leverage and power.
And so prices exploded from $30 per megawatt hour in 99 to peaks of over $1,000. The utilities were now buying power at 20 cents per kilowatt hour and forced to turn around and sell it at 6 cents. They were bleeding money on every customer. You know, what's interesting about this is California bundled it in exactly the same opposite way that they did with the wind issue. When they locked in those wind contracts, they thought there was no way that prices would go down. And in this case, they thought there was no way that prices would go up. It's like they never learned their lesson.
And what happens when you try and constrain a market? You have actors that find ways to manipulate it. Enter the greatest market manipulator of our generation, Enron.
Enron. Well, let's go back in time and we'll see that Enron was actually involved in multiple steps of restructuring. You had Ken Lay, the CEO. He helped lobby heavily for the 92 EPA Act and served on Bush's Energy Task Force. Enron helped create the first real spot market. And by the late 90s, Enron Online was handling 25% of all of that real-time energy trading. Fortune had named it the most innovative company 6 years in a row, including in 2001, the year it filed for bankruptcy. So what did Enron actually do to manipulate the markets?
They were able to do things with the electricity markets that you can't do with commodity markets. For example, they would buy up transmission rights on critical paths and then claim that the line was congested, not by actually using it, just by saying it was full. And then they would graciously accept a payment to free up the capacity that was never actually constrained, right? They devised all of these different strategies, names like Death Star or Get Shorty, selling power they didn't have, or overscheduling demand.
One of the darkest moments that I read about during this time is there's a moment when there's a forest fire that's shutting down transmission lines, and Enron's on the positive side of the trade that's going to lead to. And the traders are overheard saying, "Burn, baby, burn. That's a beautiful thing."
The strategies that these Enron traders concocted were mind boggling and lacked any sort of appreciation for what they were actually impacting on the other side, be it hospitals that needed power or homes that needed power. If you want to learn more about the Enron story, the Acquired episode on them is absolutely phenomenal, and you will tear your hair out listening to it.
What's somewhat surprising is that ultimately what gets Enron in the end is none of these trading shenanigans. It's actually the problems they have with internal financial accounting. In a really deep echo of what happened with Insul, Enron had been cooking its own books. And sure enough, an Arthur Andersen accounting firm is involved in the scandal, and quite the opposite, they never again regain their reputation. But throughout all of this, the amount of real human impact is staggering. We had to have rolling blackouts that swept California, not from storms or physical fires or physical outages, but from a failing market design. Meanwhile, LA's municipal utility, which was never deregulated, kept its lights on and actually ended up selling power over to the private utilities, their neighbors who are struggling in this moment.
And during this time, California lost anywhere from 40 to 70 billion dollars of excess electricity costs, which is essentially a transfer of wealth from the California ratepayer to the energy traders.
And so PG&E ultimately declared bankruptcy in 2001. Governor Gray Davis said, quote, California's deregulation scheme is a colossal and dangerous failure. It has not lowered consumer prices. It has not increased supply. In fact, it has resulted in skyrocketing prices, price gouging, and an unreliable supply of electricity. In short, an energy nightmare. The next year, he was recalled from office due to the mismanagement of this entire crisis.
Everyone across the country is looking at California, and the reaction is a unanimous retreat from further innovation. And eventually, Congress passed the Energy Policy Act of 2005 to respond to all these crises.
So here we are in the early years of the 2000s, and let's just remember what has hit us as the industry. The mood was exhaustion and caution. After the California debacle, after Enron's collapse, after the dot-com crash, and after 9/11, people wanted the grid just to work. No more experiments, no more clever financial engineering, no more promises about how the markets are going to make everything better. Just keep the lights on and keep the prices reasonable. But that's not how history always works.
So come August 2003, full heat of the summer in Ohio, and a few overgrown trees brush against a transmission line in Akron. This sets off a cascade that would knock out power for 50 million people across 8 states and part of Canada within minutes. What could have been a minor localized outage instead spread to almost 100,000 square miles. And there's one company at the center of it all.
First Energy. And here's an example of what this restructuring in utility economics had wrought. In 2002, First Energy had completed only 17% of their scheduled maintenance. They had a backlog of over 11,000 maintenance items. They'd laid off 500 skilled workers and linemen. They'd stretched their tree trimming schedule from every 3 years to every 5, all to cut costs in this newly competitive market.
I think I remember reading that the distance that the vegetation needed to be from the line went from like 3 feet to 6 inches. I mean, everything was moving in the wrong direction. And so when those Ohio lines tripped offline, electricity surged in all directions. We've seen this before, what happens with an interconnected grid, right?
The operators there in New York are watching 800 megawatts suddenly come sucking westward toward Ohio and then abruptly reverse direction. They described it like watching a tsunami sloshing around in a bathtub.
Each state is scrambling to protect itself by disconnecting from its neighbors. These very interconnections that were supposed to make, and that did make, the grid more reliable at most times, was the pathway to cascading outages and failures. And within hours, the lights were out from Detroit to Toronto to New York City.
And so people are trapped in subway cars, elevators, water pumps are failing, the telecom infrastructure is going dark. Everything stopped. And this blackout would ultimately cost over $6 billion in lost business revenue. You can actually see it show up as a dip on America's GDP for the year.
It ends up taking 4 days to restore power. And the reality is that a huge amount of grid control was still pick up the phone and call someone. And so these surprise blackouts actually exposed the inadequacy of the tools we were using to understand and manage some of our most critical national infrastructure.
Yeah, despite all of our technical advances, despite computers and satellites and sensors and the internet, grid operators were still flying blind while managing the most complex machine in the history of humanity with tools barely more advanced than a telephone. I think there's a story where before Microsoft, Gates and Allen had written some of the early computer code in the 70s, and BPA was still operating that code during this era.
30 years later.
That's right.
And unfortunately, this wasn't an anomaly. It was a preview. So the argument is that the age of de and re-regulation actually created a grid that was more fragile, and it shows up in an increasing pattern of outages throughout the 2000s.
Back in 2001, we had 15 significant outages. By 2007, nearly 80. 4 years later, 2011, over 300. In most of the industrialized world, the average power consumer has about 10 minutes of outages a year. And Americans now sit with an average of over 5 hours per year. And some years with bad events, the number's up to 11.
Yeah, we're getting called a superpower with a third world electricity grid, right? Things that are happening as routine on a Tuesday would be national crises in a Japan or a Germany.
And the number one cause of blackouts in the world's most advanced economy is the combination of overgrown vegetation and storms and a sneaky little animal, the squirrel. They've actually shut down the NASDAQ twice.
And so zooming out, you've got a power grid that is a system of systems loosely connected to each other, built for the weather patterns of the 1960s. The problem is 21st century storms are more frequent and more powerful, and the grid is simply not designed to handle this age of extremes. This is part of what was perpetuating these more frequent outages and a reckoning within the electricity sector.
And so finally, for the first time, FERC mandated that all the utilities join NERC, the Reliability Council, and that there'd be a focus on trees, training, and tools, including mandatory vegetation management requirements that grid systems can survive a single failure and minimum training standards and operators. It's kind of wild that it took us this long to implement these training systems.
And so while the grid is struggling to stay reliable and move power between points, we're also continuing on with this moment of flat or declining demand. And on the supply side, we've had coal, hydro, and nuclear be the staple of our generation. Now we're about to enter a whole new era of what that generation is going to look like. Let's first go to Texas.
And so for 20 years, a wild man in Texas, oil prospector George Mitchell, has poured millions into what everyone thought was impossible, which was extracting natural gas from shale rock formations deep underground. And everyone thought he was being foolish. But he combined hydraulic fracturing with horizontal drilling and seismic imaging to unlock what's now known as the fracking revolution.
So in 2000, shale gas was just 1% of our production, right? It wasn't even on the radar. By 2009, that hit 14%. And by 2014, nearly half of America's natural gas came from shale formations.
And people thought we were going to run out of gas, right? As recently as 2007, experts thought America would need to import natural gas from overseas. And boy, did this change that.
So what did this do? Well, as you increase supply of natural gas, the prices collapse. And at the same time, coal plants that had been printing money for decades suddenly found themselves uncompetitive.
That's right. The economics were brutal for coal. And we talked a lot about this in our coal episode. But you could build a gas plant in half the time. And now the fuel was much cheaper and these plants were more efficient. And this became ultimately a death knell to coal's dominance in electricity generation. Going into this era, coal is about half of electricity generation. Now it's down to 15%.
And interestingly enough, this natural gas boom and the death of King Coal is happening at the same time as a scientific consensus that's been building for decades was breaking into mainstream consciousness. For those of you around, remember Al Gore's Inconvenient Truth becoming one of the highest grossing documentaries in history, or Hurricane Katrina making extreme weather a front page story. Climate change and climate legislation and climate action were coming to the forefront of national dialogue.
And so we had over 30 states adopt renewable portfolio standards that mandated that utilities source a growing share of their electricity from new clean sources. Federal climate legislation remained politically toxic, but state-level policy and market momentum was accelerating regardless.
The question was emerging of how renewables would enter the grid. Now, at this point, even as late as the 2000s, the industry didn't really call it clean energy. They called it alternative energy because it was super niche. This had not hit mainstream yet. While average wholesale electricity prices were about $30 a megawatt, wind was over $100 and solar was over $350. So it was economically infeasible to imagine the benefits of this energy competing with traditional sources.
But fortunately, they didn't quite yet have to compete on their own merits. We had states passing these standards requiring some level of investment, and we had major federal production tax credits that had started in the 90s and continued to cut the cost of investment by over 30%.
We were setting ambitious targets to move the industry along, and it turns out the mandates worked well. Between state mandates pushing and federal subsidies pulling, renewable capacity exploded over the 2000s.
We went from 100 gigawatts in 2000, mostly hydro dams, to over 500 gigawatts by 2023, mostly wind and solar. And the real shock was the collapse in price. From 2010 to 2020, solar panels fell 90% in cost. This shattered the price targets that the DOE had set.
Now, we can't take all the credit for the benefit here because a lot of that price was driven down by China manufacturing a tremendous amount of capacity for export and then actually supplying their own internal needs to become the first electrostate. That amount of manufacturing they were able to build helped shape global energy markets and drive down costs more than we could ever imagine.
And so solar and wind went from these resources coming into the 2000s that were an order of magnitude sometimes more expensive than the wholesale electricity markets to being the cheapest source of electricity generation that we could add to the grid.
And here's where renewables have their secret weapon: zero marginal cost. See, once you build a wind farm or a solar array, generating that next incremental kilowatt costs essentially nothing. You don't have to buy coal, you don't have to burn oil, no emissions, no cost.
And this cost revolution of renewables, I think, is one of the greatest industrial success stories of the 21st century. Policy created this initial market, manufacturing scale and learning curves drove costs way down, and then the economics have taken over, and renewables went from needing policy to survive to being the cheapest source of electricity in much of the world.
No good success story comes without a rub. With so much solar entering the grid, it would start to produce more power than was actually needed. Why? Because electricity demand, especially in homes, follows a particular pattern. When you graph it, it starts to look a lot like a duck. You start the day consuming quite a bit. It drops down when the kids go to school and grown-ups go to work, and then it surges back up when everyone comes home.
The problem is that sunny afternoon when millions of panels are generating peak power is not when anyone needs to use it. The duck curve began to wreak havoc on markets. In Hawaii, the utility had to start refusing new solar connections, not out of spite, but because they literally couldn't use all the power. As solar installations ramped, California had to be prepared to spin up gigawatts of power plants for the evening when the sun was going down and usage was beginning to climb.
Then comes negative prices, which is kind of the ultimate sign that economics is colliding with physics. You'd have days where you're generating more power than a region could use or export. And the grid operators face this really difficult choice. Do you pay the power generators to shut down, or do you pay industrial users to consume excess power?
So by early 2021, California experienced negative pricing for 20% of midday hours. The state that had pioneered renewable energy was now throwing it away.
And as renewable percentages climb, operators adapt to market signals. So by 2023, our good friends down in Texas were running their grid at 80% clean energy during peak times, with 60% of that coming from solar. They'd basically learned to surf the duck curve because it was the most economical and profitable thing to do.
So the fundamental physics of the grid hadn't changed. Supply still had to match demand at every moment. But now that balance required a whole new dance where we took into account the rhythms of the sun and the wind into that balancing act.
So through this period of renewables development and climate concern, there was a huge attempt in the early Obama years to pass what was called the Waxman-Markey bill. Now, Waxman-Markey was a major national cap and trade bill on carbon emissions, essentially figuring out a way to use the tool of pricing to drive down carbon emissions. Unfortunately, it died in the Senate. It had narrowly passed the House by a vote of 219 to 212, but it was never brought to the Senate floor because it had no chance of overcoming a Republican filibuster.
And so with this proposed carbon tax foiled, activists decided on a new strategy. Let's go back to Nixon's established EPA and question whether or not greenhouse gas emissions should be included under clean air. This started during the Bush era, which of course pushed back, but they sued and the case eventually went to the Supreme Court, which ruled 5-4 in 2007 that greenhouse gases are in fact air pollutants under the Clean Air Act. and that as a result, the EPA could not decline to regulate them and do nothing given the scientific basis. And so, with the Obama administration in the White House, in December 2009, the EPA formally found that 6 greenhouse gases, in fact, endanger public health and welfare through their contribution to climate change.
All of this built the foundation for a proposed reshaping of the grid. It was called the Clean Power Plan in 2015, and it required utilities to cut carbon emissions over 30% below the 2005 levels by 2030. Each state would get a target and submit a plan. The rule gave states flexibility in how they met their targets because we've got to adhere to our culture of states' rights. They could shift generation from coal to natural gas, they could invest in renewables, maybe improve efficiency, or participate in these emission trading programs. And this was the centerpiece of our commitment to the Global Paris Agreement in 2015.
But it never took effect. 27 states decided to sue the EPA back, and ultimately the Supreme Court got uneasy and decided to stay the implementation. Just over a year later, Trump takes office the first time and pushes the EPA not to implement any of this. And of course, this whole basis, this whole endangerment finding was just repealed in February of this year. So it's back to the courts again, whether or not the EPA even has the right to regulate greenhouse gas emissions as part of the Clean Air Act at all.
And so we've got this back and forth. Legislation doesn't take effect, new legislation gets repealed, and all this happens over the course of a decade. But then comes the market, and the market punched back. A number of major utilities were like, you know what? We are going to follow the cheapest form of generation. So, for example, in December 2018, Xcel Energy announced a 2-phase plan to reduce CO2 emissions by 80% by 2030. It was the first major US power company to commit to net zero carbon emissions by 2050. And this came right on the heels of their decisions to shut down 2 coal plants and replace it with a $2.5 billion pledge to renewables and battery storage. They saw the future and where the market was going and decided to move ahead anyway.
And the floodgates were opened. By 2019, Duke Energy, the nation's largest electric utility, had similar net zero carbon emissions targets. Dominion came next, and then Southern Company. Wind and solar were now cheaper than coal, and the fracking revolution hit coal hard.
And so this Clean Power Plan demanded 30% cut by the year 2030. And by the time 2020 rolls around, the power sector had already cut emissions by 40% without federal climate policy at all. The market was telling us where to go.
And a small chemistry reminder here, coal is insanely carbon intensive. A lump of coal is largely a lump of carbon. You burn it and you're reacting that carbon with oxygen to get carbon dioxide. Natural gas, which is mostly methane, is CH4. So you burn that and you get 1 carbon dioxide molecule, but you also get 2 plain old water molecules. And so net, gas is less than half the emissions of coal for the equivalent amount of power generation.
And so when fracking cratered gas prices and renewables went to zero marginal cost, that dirty black rock didn't stand a chance. But it wasn't just utilities responding to economics. People were getting frustrated with our slow pace of federal climate policy as well.
That's right. So communities had gotten fed up with the regulatory back and forth and decided to take matters into their own hands. What if towns didn't have to take whatever power choices the utility gave them? If there's now this restructured market, can't a community choose to buy its own power? If Google and Microsoft can go sign these renewable PPAs and poles and wires are open for business, why can't we just band together and go get the kind of electricity we wanted?
It's a great question, and it worked. We drafted legislation and called it the Community Choice Aggregation, or CCAs. What it meant was towns could now vote to buy cleaner energy. Counties could prioritize local solar if they wanted. And the concept spread across the country: Ohio, Illinois, Massachusetts, New York. And then comes California, where it became a direct response to that deregulation, re-regulation disaster we talked about earlier.
So Marin County gets excited and proposed the state's first CCA in 2010. PG&E launches an all-out campaign to kill it. There's mailers, robocalls, community meetings, anything to try and convince customers to stay with the integrated utility model. PG&E spends over $45 million on a statewide ballot measure to make it nearly impossible for this model to work and keep the community locked into the utility. Opponents raised a massive war chest, just $100K, to counter that. And despite that, PG&E lost the vote.
And so today, over 1,800 towns, cities, and counties, serving 36 million Americans, have joined CCAs. And every community in America running on 100% clean energy is using this CCA model.
And so, if we zoom out and look across this whole time period, it's pretty remarkable. The 15 years from 2005 to 2020, we have this explosion in gas generation, the true beginnings of wind and solar, and a complete chop down of coal. Remember, 50% of US electricity was coal in 2005, less than 20% in 2020. It's almost like coal and gas swapped places in those 15 years.
Swapped places is actually a great framing because our grid basically had the same amount of electricity flowing through it in 2005 as we did in 2020. Remember that demand stagnation? It was the culmination of those major efficiency gains. Everything from light bulbs to fridges got significantly more efficient.
Yeah, I think LEDs are an underappreciated hero of the grid, right? Between 2001 and 2020, American homes cut their lighting energy use by more than 60%. Not by having less light, by having more. LEDs were just such a major technological improvement from the incandescent bulbs of Edison.
And during this time, we had more offshoring of industry. Total industry load fell by over a fifth, even while the economy was growing, because we were moving from a manufacturing to a more services based economy. And of course, we had the 2008 crisis, which totally cratered demand. And so this flat load period was actually a period of transition of our generation sources.
Yeah, and it quickly became clear that there's one more thing holding back the pace of renewables deployment. Coal and gas, for all of their immense problems, they're dirty, emittive, require constant mining and extraction. They do have some very convenient properties.
That's right. They really are a commodity. You can store a bunch of it up for use later. You can move them around. We've been shipping coal around the world for over a century. As we all know, railroads basically came up alongside the coal industry.
Side note, did you know that 40% of global shipping is just moving fossil fuels around?
Just moving fuels back and forth.
That's right.
And of course, gas. You stuff it into a high pressure pipeline and you ship it off.
And then just the whole model of thermal generators with this stored fuel and spinning turbine is a highly dispatchable resource. Meaning when we need or want more or less power, we can easily turn them up and down.
Now, on the flip side, to take full advantage of the immense wind and solar resources of our country, we know we're limited by our transmission infrastructure.
Especially if you want to smooth out the duck curves we were just talking about. You really want to overbuild and aggregate solar with wind across multiple regions, which requires more and more transmission.
Totally. But before we could fully reckon with expanding the transmission system, we need to take stock of the aging infrastructure that we do have. And the aging transmission system was beginning to cause some serious havoc.
So it's 1921. A young 16-year-old utility is competing to electrify the booming NorCal market. The utility is Great Western Power, and they build a transmission line cutting through the Sierra Nevadas. And on this transmission line, they use a small C-shaped hook, about an inch in diameter. It's bolted on the tower to hold the conductor off of the tower's arm. And it's made of a cast iron, a material that the manufacturer would, a few years later, replace with steel when they discover that it could become brittle with age.
And it'll just hang there for 97 years, holding up the conductor through the Great Depression, through their merger with PG&E in 1930, through decades of war. But millimeter by millimeter, a notch gets cut into the curve of the hook. In November of 2018, it snaps. The campfire that followed killed 85 people and essentially erased an entire town. 18,000 structures gone in the deadliest wildfire in California history. For California, it was a climate reckoning into the entire utility model. An investigation opened up into PG&E, and the results were not so good.
That's right. In the 5 years before this happened, PG&E had in fact issued $5 billion in shareholder dividends while deferring maintenance. After the fire, PG&E inspections revealed that 250,000 repairs were needed across their system. This line would be turned off, never to run again. The company that had kept the lights on for 16 million Californians declared bankruptcy yet again. And so PG&E pled guilty to 84 counts of manslaughter and negotiated over $25 billion in settlements during this bankruptcy.
The fundamental problem is that utilities have very little incentive to overhaul operations that have been working reasonably well as monopolies, right? They're not subject to the relentless competition that drives normal, unregulated companies to improve and innovate. And their poor track records don't often result in much more than a power outage here or a gas leak there. And unfortunately, it can take a massive catastrophe to reveal the full extent of the underinvestment they've had over years and years and years.
And so, with fire seasons getting worse, we needed an immediate plan. PG&E's core solution was called public safety power shutoffs. What does that mean? It means when fire danger spikes, when there's concern of a fire season, they would simply turn off the power lines to millions of customers, sometimes for a couple days at a time.
You'll hear energy nerds call this PSPS.
PSPS. And so in October 2019 alone, over 2 million Californians lost power during these planned blackouts.
The first shutoff they attempted affected about 1 million customers because PG&E couldn't target precisely enough. Now, they've now refined their systems to shut off power to specific feeders, but it still impacts thousands, if not millions. The long-term fix would be to find a way to keep lines largely online, but stop them from being able to spark fires. So there's been a massive investment in what's called undergrounding lines.
And when a utility hears investment, they see ROE. And the outcome of this disaster is that PG&E has since committed $18 billion in wildfire mitigation capex through 2025. Undergrounding costs an immense amount, $3 to $4 million per mile. But the vast majority of this expense goes back into the rate base. The utility earns 10% ROE, meaning that the more PG&E spends on these safety investments, the more it earns. You might think that leads to a good incentive to invest in more fixes, but it could also lead to an incentive to choose the most capital-intensive solutions, which many claim undergrounding lines might be.
And who pays for all of this? We do, the ratepayers. In California, we have some of the highest electricity costs in the entire US, and wildfire-related expenses represent a majority of that increase.
Yeah, and so we've talked a little bit about this kind of utility economic model, but this seemed like a good point to pause and make sure we spell out exactly how the various accounting buckets work inside of the utility's balance statement. So let's go inside a utility. How does an investor-owned utility actually make or not make money?
This is some of the wildest business economics I've come across.
Yeah, it's very unique. Well, let's start with CapEx, which is what we've been waving our hand at quite a bit. This goes into the rate base and earns this return on equity, or ROE. This is any physical assets the utility builds or buys. These are the coal plants, the power lines, the investments to underground those lines. These all go into the rate base.
And so, as regulated entities, these utilities earn a set authorized return on equity, which is typically about 10%, on the base for the useful life of the asset. And these assets last for around 40 years. They also recover depreciation and cost of debt. This is the earnings engine. The bigger the rate base, the bigger the earnings.
The next bucket is operating and maintenance expenses. These are things like the day-to-day costs to run the system. And these are recovered dollar for dollar from ratepayers. These are effectively economically passed through to ratepayers.
So a utility needs to trim some trees, do vegetation management so that trees don't fall on lines, do line inspections, crew labor, emergency repairs, customer service. All of this is cost they could just pass directly through.
And same exact goes for any fuel or purchase power, right? It's all just passed through directly to the customer. So they're not making margin on it. It's not like their sweet CapEx margin, but it's not like they're losing profit on it either.
No, it's amazing. They just pass it on through.
Okay, and then we have the last bucket. It's called shareholder absorbed costs. These are things where they get no recovery. And these are effectively costs that regulators decide to disallow. They say that that particular cost is not useful in any direct way to ratepayers, and so it's outside of any recovery mechanism. And there's a bit of an industry-wide consensus that typically forms. Despite our balkanized regulatory structure, you start to see things like, oh, everyone's kind of settled on the same ROE rate. Why is no, utility regulator settled somewhere closer to, the market rate of 6 or 7%? You can tell that the same playbook is being played across the country.
Yeah, it's very hard for these PUCs with their limited resources to actually stretch beyond and try something new. But the counter argument is, if they don't do it, who will?
You zoom out, ultimately, you can see how all of this kind of stack up of incentives do get out of whack, right? The utility is being quite literally rewarded for anything it can put in the increasing CapEx bucket to get ROE. And the only exception tends to be performance benefits if you do things like shrink your maintenance budget. And that can lead to things like less care for vegetation.
And to make matters even more complicated, the PUC and these utility commissioners are subject to the legislature, which is subject to changing political winds in our state democracies. And that means that these massive private utility companies have a major incentive to be active participants in our political process.
Now, everything we just described is how investor-owned utilities work. And those are serving almost 3/4 of American electricity customers. But they're not the whole picture. We still have almost 1,000 rural electric co-ops and about 2,000 municipal owned utilities scattered across the country. And their economics are fundamentally different than the IOU structure. There's no shareholders, no return on equity. Co ops are owned by their members, by the customers themselves. Munis are owned by the local government. They're able to borrow at low rates because they're nonprofits or government entities. In a lot of cases, they just buy their power wholesale and distribute it. There's no capex earning engine. There's no incentive to build these gold plated projects, which sounds great and like it could solve all problems, but every ownership model has its potential complex incentives. Co ops can end up locked into upstream contracts with power suppliers, chaining themselves to legacy generation. Munis can end up either underinvesting to keep rates low for political reasons or potentially shifting utility profits into the city's general fund as a hidden tax. And so ultimately, every model has some version of an incentive problem, and IOUs are still driving the utility relationship for most consumers in America.
So, coming out of this fire season, it became abundantly clear that we were in a new era of life as a utility in the increasingly dry western part of America. But changing and weirding weather wasn't done for the US grid.
And so we've mentioned ERCOT and Texas's unique structure a few times, but here's what it looks like in practice. Inside about 80% of Texas is a single grid and regulatory structure called ERCOT. And it's false to say that grid is a complete island, but the ties are very small. There's just over a gigawatt split across 5 DC ties. For context, peak demand in ERCOT has hit 86 gigawatts. So you're not going to be able to do really anything significant to draw from those ties if you need it in a pinch. And in 2021, Texas really needed it.
They sure did. Many of you might remember this. Our listeners in Texas are going to remember this vividly. It's February 2021, and Winter Storm Uri hits the state. Energy infrastructure across the state gets locked up. Gas wells freeze, coal piles turn into frozen blocks, wind turbines get iced up. Even one of Texas's 4 nuclear reactors was knocked offline. The impact is massive. 30 gigawatts of generation capacity taken offline. It's about a third of their grid. And meanwhile, the rest of the remaining load is physically pulling harder and harder on whatever generators are online. So they start to slow all the way down to 59.3 hertz, which, if you remember how sensitive things are, we need to keep it running at 60 hertz exactly.
So apparently, if they didn't start cutting off load, they were less than 5 minutes away from a complete grid failure, meaning the turbines stop. They stop spinning and they have to figure out how to restart the grid from what's called a black start.
Not an easy decision. Either you start cutting down the limited generation you have, or you risk a full blackout. And this is sub-zero temperatures. Millions lose electricity. Over 240 people actually died.
And the economic damage from this storm was estimated around $100 billion, making it the costliest natural disaster in Texas's history. Despite this disaster, the political desire for independence remained strong. Former Governor and Energy Secretary Rick Perry said, Texans would rather go without power for longer than 3 days than have the federal government involved in the state's power grid. So California and Texas, 2 very different crises, but the same lesson, I think. The grid we built for the 1970s was breaking under the weight of our changing climate.
My goodness. And so if we think about what's happening during this era of 2005 to 2020, you've got America completely transforming its power supply. King coal goes from half of our electricity to less than 15%. Natural gas surges. Renewables go from an alternative energy source to the cheapest source on the grid. And battery costs collapse 90%, all while we cut emissions by over 40% without any federal policy.
So on one hand, there's so much dynamic change, but the actual core wires, the institutions, the planning processes, they were largely locked in from the same basic economic structure in an era of somewhat calcified growth. Every previous era in this story had both technological and institutional innovation working together, right? We had Edison and the light bulb designed alongside the central station business model. Insull unlocked larger steam turbines alongside his growing regulated monopoly structure. The New Deal, we saw the building of these massive federal dams through these new innovative agencies like TVA and BPA.
But this era of the 2000s was a mirror image, right? We had technological revolution on the supply of our energy, but nothing on the institutional management. And the reason we managed? Flat demand. Because when electricity is flat for 15 years, you don't really need to invest in new transmission. You might want to, but you can kind of manage without it. And so you don't really spend the extra effort of political reform and planning process reform. You can kind of go a little longer without solving the issue of interstate siting.
And I think this was simultaneously a gift and a trap. It bought us the 15 years to begin to decarbonize and transition the power sector without confronting any of the hard institutional problems. And that also meant then we had 15 years where our muscle for building big things began to atrophy while our grid aged.
We wanted to understand, how unique is this American grid story? What else can we learn about it if we look outside of the US? And so we thought of the obvious juxtaposition to the US, which is China. China's electrical infrastructure at mid century looked a lot like America frozen in the 1920s. Isolated utility territories serving individual cities, no unified backbone connecting any regions or coordinating across provinces. And it was about to get much worse.
That's right. Mao's ideological planning process didn't just slow progress, it ended up actively reversing it. His big theory, and we talked a lot about this in coal, was that instead of building railways to ship coal from the resource rich north to the populated south and east, people should simply dig and use coal wherever they lived. Find and use your own energy locally and be self sufficient.
And the result was predictable and catastrophic. Very little coal, very little power. An entire nation held back by energy poverty. While the rest of the world electrified, China's rural communities lacked fuel to even cook a meal a day.
And so, to put some numbers on this, in 1980, China's GDP per capita was only $200, and its whole grid capacity was about 66 gigawatts. America's GDP per capita was $12,000, and its grid capacity was 600 gigawatts, almost 10 times larger.
And even into the 1980s, China operated a patchwork of 6 regional networks and several unconnected provincial grids. No province could reliably share power with its neighbor. No region could help another during shortages. This electrical system was just these isolated, underdeveloped islands.
But in the late 80s and 90s, China began a massive build-out campaign to reverse this. They nearly tripled their grid. They built the equivalent of one new medium-sized power plant every 2 weeks. China was about to compress a century of electrical development into just a couple decades.
And then in 2002, China's State Council announced what looked like a familiar move. They were going to break up their monolithic state power corporation, separate generation from transmission. For a moment, it seemed like China might have caught the bug that was passing around the US in the 90s and embarking on a playbook of restructuring.
Not quite, though, right? American restructuring separated transmission from generation by fragmenting control across thousands of competing utilities in this web of regional organizations. China instead created 2 massive state-owned grid companies that owned all the transmission and distribution.
Simple. And this centralization is what has enabled China's effective industrial strategy of the grid. The larger of these 2, the State Grid Corporation of China, covers a whopping 88% of China's land area. This company employs over 1 million workers and serves over 1 billion people across the country.
The state council gave these grid companies clear mandates. We need to connect the country, modernize infrastructure, and enable economic growth.
Why? Because a large landmass like China faces the same problem that every other large country does, including the US. Energy resources to generate power were thousands of miles away from the people and factories that needed to consume it.
And so for China, we had these massive coal deposits in the northwest, incredible hydro resources in the southwest, endless wind and solar across the western and northern regions of the country. But 94% of the population lives east of what geographers call the Hu Line, packed into coastal cities thousands of kilometers away from all of those energy resources.
So with this new organizational structure, China sets out to build transmission and overcome this geographic mismatch. And unlike the US, which had to manage this myriad of interests and incremental upgrades across a complex and fragile system, China is basically able to leapfrog directly to ultra-high voltage technology. They were able to build for a future without being constrained by a past.
Welcome back, DC. So since 2009, they've built over 40 of these ultra-high voltage projects. These are transmission lines that operate not at tens or 20s of kilovolts, at 800 kilovolts, 1,000 kilovolts. To put that in perspective, most American utilities get nervous above 500 kilovolts.
One example is the line from Xinjiang to Anhui, which runs at 1100 kilovolts DC, carrying electricity over 3,000 kilometers. This is basically like running a large power line from Boston to Denver with the output of 12 large power plants, or enough to power all of New York City. And when that line was built, it was moving 50% more electricity 600 miles further than anything else built in the entire world.
And us in the US, we have zero ultra high voltage transmission lines,
Not a single one?
not a single one. So, I mean, if we go back to the 1890s, let's remember that Edison lost the war of the currents because DC couldn't travel long distances. So, what are we talking about with these high voltage DC transmission lines? Well, the key, if you remember, is that AC could transform. AC could be stepped up, sent hundreds of miles, and then stepped back down for consumption flexibly and without losses. But now in the modern era, we have something new. We have power electronics that have now solved Edison's problem. We can actually send DC thousands of miles. And it turns out that DC is actually even more efficient than AC over long distances. And so today, what we actually need and want is AC and DC both working together. The ultimate grid of the future is this hybrid. On the generation side, you have solar panels and large batteries putting out DC, being transmitted over long distances in these ultra high voltage lines. Then at the local distribution grid, you're still using the AC to transform it. But then back at the house or the office, you're often converting back to DC to charge a battery or run a device. So the grid is actually an AC sandwich between these two DC systems.
China didn't just go big, China went fast. China's first ultra high voltage AC demonstration project went online in January 2009, just 2 years after starting the project, which is something that would probably take us over a decade.
It's not just about transmission. In 2025 alone, China added 430 gigawatts of new wind and solar capacity. The US the same year added 63 gigawatts of all technologies. China was operating at nearly 7 times the pace.
The contrast between the American and Chinese grids is more than just technological. You could argue China finances and regulates power as infrastructure, like highways and ports. Power is an instrument of their industrial policy and a tool for building national wealth.
You know, it's a funny echo. Like, I think China's treating their whole grid similar to how we treated the Tennessee Valley Authority or Bonneville, right? As tools for nation building.
That's right. And apart from those big exceptions, American power is treated more like a consumer good. It's priced by the market like a commodity, wheat or copper.
When China decides that it needs an ultra high voltage line, they acquire the land, the state grid builds it, and it's infrastructure. Versus in the US, we look at it and we decide over and over and over again, should this project even happen? Have we listened to everyone? And usually the answer is we're not going to build it.
Yeah. Now, it's not all pretty in China from a grid perspective. They had renewables hit almost 60% of total installed power capacity, solar and wind turbines operating in the deserts, and plummeting costs of their manufacturing. And yet, fossil fuels still generated almost 70% of their actual electricity.
It's an immense amount of coal still being burnt in China.
Yeah. Why?
Well, the provincial governments favored their own coal generators over importing wind power. And so the local coal plants meant local jobs, local tax revenue, local control, and shutting down a coal plant to buy faraway wind power is political suicide for a provincial governor.
And so what's the result of this? China has to curtail fairly aggressively. Curtailment means that they have to waste the clean electrons that they're generating. Sometimes because the grid can't absorb it fast enough, sometimes because the dispatch rules are actually prioritizing these coal plants that you just mentioned.
And so let's leave the China story with where they're going. They're actually going to launch some new market testing. They're going to launch this unified national power market to incentivize provincial leaders to buy those cheap wind electrons and sell those locally.
It's worth noting this isn't their first time using financial incentives to drive adherence to policy. They actually have a national carbon market that covers over 2,000 power companies producing 40% of national emissions.
And their next 5-year plan is doubling down on these ultra high voltage lines, connecting the Southwest hydropower and the Northwest solar with the eastern cities.
Yeah, China's basically recognized that electricity is superior to combustion, and it's deliberately electrifying everything. And they're not busy calling it clean energy or renewable energy or green energy. To them, it's just new energy, and they're going to build it.
Certainly not alternative. It's the new and better thing. The thing is, the China model requires a particular political economy, A real tolerance for central authority, a willingness to subordinate the local interest to the national goals that few societies possess.
Yeah. So it's a little bit less about which model is right and a little bit more about which model is the most effective for the society that they have. For example, in Australia, they're operating the highest penetration of rooftop solar in the world. 1 in 3 homes have it.
You look over to Pakistan, and it's importing massive amounts of cheap solar panels, equivalent to roughly 40% of the country's entire grid capacity in a single year. Not because the government planned it, but because millions of people thought it was the right choice for them.
You look to Germany and its sovereign wealth funds that finance transmission lines from the wind farms in the north to the factories in the south.
And Italy is pulling power from French nuclear facilities to power their summer air conditioners.
And Brazil is getting about 60% of their power via these massive transmission lines from hydro deep in the interior.
Meanwhile, in America, we have this amazing system that we built for the 20th century, and we have to figure out what we're going to do to make it work for the rest of the 21st.
Amazing. All these slightly different models for different historical contexts and different political environments.
So let's go back to what's facing us here at home in the US today.
Now, we spent the years leading up to 2020 talking about all the factors that have led to this period of flat demand.
From increasing efficiency to the greatest recession, and the outcome of that, plus the prior 20 years of relatively low growth, is that the entire grid apparatus, every regulatory structure, every technology choice, every permitting process was structured around this reality. Planners planned around US load growth at roughly 1% or negative for decades.
And then in a flash, everything changed. Between 2022 and 2024, utilities' load growth forecasts jumped nearly 5 times. The assumption of stagnation was over.
And what was happening? You had the electrification of everything from vehicles to indoor heating. You had the onshoring of manufacturing fueled by the CHIPS Act and the Inflation Reduction Act incentives.
And of course, the growth of data centers. In the next 15 years, we were saying we would need 2,000 more terawatt hours for the grid. PJM, the largest grid operator serving 65 million people across 13 states, expects power demand to grow at nearly 5% per year for the next decade.
So, how does this translate into the power markets? Well, PJM's capacity market has settled at around $29 per megawatt day. Last year's auction cleared a staggering $329 per megawatt day, over 10 times higher, sending a clear price signal that we need more capacity.
The CEO of Exelon, serving over 10 million customers, captured the moment perfectly. The energy industry will go through more change and transformation in the next 10 years than it has in the last 100, which is saying quite a lot.
The last time America saw real significant load growth like this was in the 60s through the 80s, when we had the rise of air conditioning that transformed the Sun Belt. But the current institutional configuration of the grid that we've talked about, the RTOs, the ISOs, the competitive wholesale markets, has never been tested under the conditions of rapid growth.
Now, with all this new demand coming on, we do have some good news on the generation side, with solar going from an alternative energy to a mainstream power producer. It's helpful to put some numbers to contextualize it. In 1977, a solar panel cost $76 per watt, which means that powering a single house would have cost more than buying the house itself.
But by 2000, that price had fallen to about $5 per watt. Still too expensive to compete with most of our other power sources, but making a lot of progress.
And then the learning curve took over. In Germany, you have aggressive feed-in tariffs that created this first mass market for solar. And China enters a manufacturing boom and scales production relentlessly. So what happens is every time they doubled global production, it drove down costs about 20%. It's actually a pattern so consistent it has its own name.
That's right, it's called Wright's Law, which just simply means that the more units of something you build, the cheaper it gets. The cheaper it gets, the more you build. And this is a classic learning curve. You just get better at doing it.
And so by 2010, solar modules are down to $2 a watt. Then in 2020, we're under 30 cents. And today we're roughly 13 cents. We're talking about a 99.8% cost decline since the late 70s.
Yeah, I think no energy technology in history, not those massive scaling coal plants, has ever experienced anything remotely like this. The end result is that the world has installed more solar power in 2023 than it did in the 63 years from 1954 when it was invented to 2017.
And it's a story of economics. Solar is now the cheapest source of electricity in most of the US, and in many places without any subsidies at all. In ERCOT, Texas's market, where price signals drive investment decisions more purely than they do anywhere else in the country, the transformation is vivid. On peak days, the grid now runs about 60% solar.
The other big shift that is happening right now is the story of electricity storage. As you recall, the entire grid is built on the physics that you have to match generation to the moment of consumption at all times, since power cannot be stored until now.
Batteries transform the fundamental physics of the grid. They can respond in milliseconds and provide power when you need it, independent of the generation source.
And this is especially important for solar, right? If you have that duck curve, you can now charge in the afternoon when the sun is blazing and discharge it right immediately after when you need it in the evening when everyone's coming home to plug in their EVs or cook dinner.
And battery costs are following the same learning curve that we saw in solar. Costs are down 90% since 2010, this time driven by Tesla, BYD, and the global auto industry. Basically, EV manufacturing has scaled battery production, and the grid is now reaping the benefits.
That's right. The US nearly doubled its existing 15 gigawatts of battery storage in 2024. And in just the first 9 months of last year in 2025, nearly 50 gigawatts of grid scale battery storage came online globally.
And then there's nuclear, a technology the grid abandoned after the cost disasters of the 70s is now coming back into vogue. You've got big tech hyperscalers who have signed unprecedented deals for new nuclear capacity because they are just desperate for baseload for their AI data centers.
And there's a hope that new technologies like small modular reactors that can be factory built instead of custom constructed on site can start to have some of that rights law kick in. And so whether that hope is justified or whether nuclear is about to repeat the most expensive lesson in grid history is one of the defining bets of the next decade.
And so, in the span of roughly 15 years, the American grid went from a system where virtually all electricity came from these large, centralized, dispatchable fossil fuel and nuclear plants to one where solar is the cheapest new source of generation. Batteries are breaking a 150-year constraint on the way electricity can be stored, and nuclear is being reconsidered for the first time in a generation. The generation mix is transforming faster than at any point since coal displaced wood in the 1800s.
Beneath all of the supply revolution, it's worth remembering a deeper truth. In the US, electricity is about 20% of total energy consumption. The rest is combustion, gasoline in our cars, gas in furnaces, coal and gas in industrial processes. The imperative to electrify more of those processes is clear. Now enters the collision that we covered on our last episode. There we talked about it from the perspective of the data center build out running into the grid. Today we get to flip that perspective.
Let's give you a quick refresh. In 2024, data centers consumed 183 terawatt hours of electricity. That's nearly 5% of America's total power supply. And forecasts for what comes next are all over the place, but many projections have that 5% more than doubling by 2030.
And the only thing analysts agree on is that every new forecast is higher than the last one. No one really knows how high this is going to go.
But the story is more about concentration. Loudoun County, Virginia, is the world's largest data center hub. These facilities consume 26% of their state's total electricity supply in 2023. A quarter of all power in that state flowing into those servers and racks.
And where there's power available, there is now a race to hook it up. Our friend Brian Janis calls this the watt-bit spread, which is the economic spread between the value of power capacity for the land and the value of the compute resources that you could build on it.
That watt-bit spread meant that hyperscalers would pay almost anything for power because the revenue potential from selling the AI compute is multiples higher than the cost of the power. So while a factory might balk at electricity prices that go 5 cents above their normal kilowatt hour price, data centers would happily pay multiples of that.
That's right. The real costs, the really significant driving costs are the chips, the researchers, and the time of being late to market. Power costs are a distant issue on that list. Time to compute is everything in the AI race.
And as Satya Nadella from Microsoft says, the biggest issue we are now having is not the compute glut, it's a power glut. It's not a supply issue of chips. It's actually the fact that I don't have the warm shells to plug into.
In the impatience to connect, we've seen 3 models emerge for how data centers would get their power. You have the traditional approach, grid connected. This means going through the normal process of submitting to a utility, getting your data center hooked up. And this, to be clear, is how most data centers that are currently operating have been built. The challenge is that a lot of the available capacity has gone away quickly. There's starting to be a backlog that has stretched from long to extremely long.
Now, we are still seeing savvy operators find opportunities within this traditional approach, namely utilizing the capacity we already have. But we'll talk about more of that in a moment. Then you've got hybrid models with power generation on site. So this is gas turbines, fuel cells, sometimes solar arrays that are behind the meter and supplement whatever grid connection they could get.
And then we have full off grid. There's a few facilities that have gone fully off grid or kind of as prototype, but it's actually close to zero that are truly entirely off grid. And so, the closest I think example of this is what XAI did in Memphis with Colossus One. They brought in 35 unpermitted turbines that are running at over 400 megawatts to power the whole thing. And they still had a small 8 megawatt grid hookup. And in the year that followed, the grid connection was actually upgraded to 150 megawatts. So they essentially started off grid, but really settled out into the hybrid setup. Turns out people really like the grid stability.
And this whole issue of how data centers are going to connect to the grid and where the power is going to come from has really broken into the political zeitgeist. And it's gotten supercharged recently with Trump gathering the tech heads and having them commit to bring their own power.
But if you zoom out on this, I think there's a little bit of a missed framing. First, for data center operators, it's not just about having some source of power generation on hand. They've had power backup for decades, generators, even batteries. It's that the primary hookup to the grid has been a phenomenal thing for them. The grid gives them highly reliable, cheap power that can be sourced from the power sources that they want to use. It's also great for the grid.
Yeah, you think about Samuel Insull's dream customers. That would make the whole grid better utilized, drive down costs, increase network value. And data centers are that. Data centers are basically the aluminum smelters of our time.
That's right.
Now, one way to look at this is we have the opportunity of a generation. We've got all these challenges with the grid, and now we've got this new surge of demand coming from highly priced, inelastic customers. Customers that want time to power. They need it fast, and they're willing to pay for it. They're also interested in renewable energy and willing to pay their fair share to upgrade the grid. So the opportunity here is to leverage this new demand and integrate it into how to make the grid more affordable, accessible, and reliable for everyone.
Yeah, I think that's spot on. I think we haven't had a moment quite like this, perhaps since the war eras when we were so mobilized to upgrade our infrastructure. What is actually slowing us down?
Mm.
Well, what's slowing us down is that you need to wait in line. Let's talk about the interconnection queue.
So the interconnection queue is a fairly wonky thing that's now making the news. It's essentially a line you have to stand in to connect a new power source to the grid. You get in line, you run a number of studies to ensure there's grid stability. And only then, once approved, are you able to connect this new power source into the grid and ensure that it's stabilized, synchronized, and can get up and running.
And who runs the line? Well, it's part of that same structure we talked about back in the day, right? It's the RTOs and ISOs, the PJMs, the CAISOs. If you're in a region that isn't served by those, then it's the utility in your region that is in charge of making sure that if a new generation is hooked up to the grid, that it's going to work, that the power flows are going to flow, and that the transmission lines can handle it. So it's there for a good reason, but the queue is starting to get congested itself.
And as a side note, historically, there's not really been an interconnection queue for load, for the consumption of energy. Because until recently, if you wanted to show up and connect your 10 or 50 megawatt load, you would just work with your utility and it wasn't a huge concern. But all that's starting to change with increasing demand coming on an increasingly stressed grid.
That's right. And the queue is now this enormous long line, but what's weird about it is it's partly fictional. So at the end of 2024, we saw roughly 2,300 gigawatts of generation and storage capacity that was waiting to connect in the grid, right? Waiting in line. For context, that is twice the country's entire installed generating capacity. Good news for us decarbonization fans, over 95% of what's in the queue is clean energy.
But interestingly enough, only 13% of everything that entered the queue between 2000 and 2020 ever got built. So lots of projects are getting submitted to just to hold a spot in line. So you get that spot and then the developers go out and do the work. But often they're filing the same project in multiple regions simultaneously, looking for the best path forward. And so this queue is artificially long because you've got your grocery cart spread out over multiple lanes.
And not only that, but it actually clogs it up, right? Because the utilities have to run these complicated studies, and then phantom projects clog the studies, and then they pull out, and then that changes the results of the study, right? And so the queue breeds the very congestion that is making it worse.
And so supply and demand on both sides are broken. Clean energy generators can't get onto the grid because the transmission lines to carry their power don't exist. Meanwhile, data centers can't get reliable power commitments because the grid isn't designed for their scale or their speed.
Yeah, and for context, these things are also operating at two different time horizons, right? A data center, once it breaks ground, usually gets built and is up and running in 1 to 2 years. New transmission takes at least a decade. To put some finer points on this, ERCOT's large load queue nearly quadrupled, with 80% of it coming from data centers that wanted power by 2030. So the infrastructure timelines and the business timelines are just living in two completely different zones. And this is actually a quick echo of what we talked about with Crusoe and how vertical integration can help you move faster. If you can look at power, the building, and compute as one integrated problem instead of three separate ones, you can actually move more quickly. And it's great that they're now thinking about what parts of their stack they can bring to the rest of the industry to help unstick other projects. But back to the system wide problems here.
Now, across the board, the problem is that we're building transmission at a fraction of the required pace. In the early 2010s, we were adding almost 2,000 miles per year. That's not bad. But by 2023, we couldn't even build 500 miles. And recent studies are saying that we actually need to build 5,000 miles just to hit our goals.
And most of our transmission spending, something like 90%, has gone to local reliability upgrades, patching the existing system that we have rather than expanding it. We're spending more money on transmission than ever before, but building less new transmission than at any point in modern history. You zoom out, and this whole clogged queue is a manifestation of the mismatch between America's ambitions for its energy system and its institutional capacity to actually build it.
And so, why can't we move faster and build faster? Goes back to the fact that there is no other country on the planet with a grid as fragmented as ours. Right, we talked about China and their transmission centrally, Brazil, France. They're all able to make a decision and move forward. Here, we've got 50 regulatory fiefdoms, each guarding their own turf. And you can trace this mess directly back to Puka's legacy in the 1930s when we dismantled those holding companies but kept the territorial mindset because it was just the politically viable thing to do to manage states' rights and federal regulation.
When Michael Skelly's Clean Line Energy spent over $200 million trying to build this exact kind of line, it was killed by one state with local opposition in Arkansas. And this was a state that was unhappy that the line was crossing over them and just passing through.
And so you might be wondering, okay, we realize that there's this generation consumption gap. And we realize that in order to build our economy at the pace we want to, we need to build transmission. Great. Well, shouldn't we have tried to do something about that already? And the answer is yes. We have tried to address this historical accident from the 30s, but we just haven't done so very successfully.
In 2005, we passed the Energy Act that gave the Department of Energy authority to designate national interest transmission corridors. Sounds great. Like, that's the whole point. And it said that if a state didn't act on a transmission proposal within a year, that FERC could then step in as a backstop to make a decision.
And so, this sounds reasonable. But then a few years later, a court ruled that a state rejecting a transmission line proposal counted as acting, which meant that the FERC could only step in if the state completely ignored the proposal in the first place.
And so it wasn't until 2021 that Congress updated the rules so that FERC could actually act in that year and push back on a state's decision. But it's not that simple. It still comes with quite a number of bureaucratic loopholes to jump through, right?
Yeah, you've got to designate a national interest corridor, and that triggers a full NEPA environmental review, which then is subject to its own litigation, which takes multiple years just to draw lines on the map. Then, once you've drawn the lines on the map, a developer has to propose transmission lines to the state agencies. Then, the state agencies have about a year to act or reject it. And if the state rejects it, FERC must then exercise its own discretion to step in and overrule the state. And then if somehow FERC does decide to do this, it has to go its own permitting process before you even start to put any steel in the ground.
Wow. We are not going to build. We are not building
We're
anything.
not
And this is
building anything.
why. I feel like you're pissed off.
It's unconscionable.
And this is the whole thing. This is holding up everything.
And if that wasn't bad enough, there's a whole issue that we don't know how to actually allocate costs for these types of things. And this turns into a massive problem where there is no standardization and we just don't have the federal entity or national interest that comes through and says, this is how we're going to get it done.
Let's say we pull that off. You still have the issue that in some regions, for example, the Southeast, the vertically integrated monopolies are not necessarily that excited for cheap power to come from some other source, right? They like that they have their own territory.
Yeah. And so this is where the utilities use enormous political influence and lobby against any federal transmission siting authority. So those cheap electrons blowing in from Kansas would undercut the coal plants in Georgia. So even if we wanted to do something about this, now we've got to deal with the tremendous lobbying efforts that are going to break down any sort of national interest regulation that we attempt.
So why aren't we building to our ambitions? Well, we talked about the interconnection queue getting clogged up. We've talked about the lack of transmission build out, but we've also been very inconsistent in our federal policies encouraging the build out of things that we want.
We've tried, but the whiplash tends to make things even worse. So in 2022, we passed the Inflation Reduction Act, which was the largest climate investment in U.S. history, almost $370 billion in climate and clean energy provisions, primarily through tax credits.
Yeah, someone we spoke to called it the Black Friday for clean energy. Instead of creating new policy frameworks, it used the ones that we had and put everything that was good on sale.
It was a blunt instrument to drive massive acceleration. And it actually did in the short term. It triggered a 71% surge in clean energy investment in just 2 years.
And then, of course, Trump comes in second time and rolls it all back with OBBB, eliminating tax credits for wind and solar projects not in construction by 2027, killing most EV incentives, and narrowing manufacturing support. So developers now faced a market that had swung between massive subsidies and sudden reversals.
And so we make these Herculean efforts, recognizing that we need federal policy, and it just doesn't land. But when projects do clear the regulatory hurdles, they start to hit another wall, which is on the geopolitical and global scale.
Let's talk about our global supply chain. So since 2019, the cost of a transformer has almost doubled, and the US imports most of those. As I'm sure you've heard, China controls the processing of most of our critical minerals. This is everything the grid needs from lithium, cobalt, nickel, and of course, rare earth metals.
And to compound that, you've got 3 companies, GE, Siemens, and Mitsubishi, that control over 75% of the global turbine market. And the gas turbine backlog is over 4 years now. So the grid is moving from bottleneck to bottleneck, constraint to constraint within this supply chain, whether it's on the transformer side or the rare earth metals that we need for our power electronics or on the gas turbine side. Everything is clogged up globally.
So if you look across all of these reasons, they're all a symptom of the fact that we were not growing for so long. So these things were issues on the margins, and now they're existential to building the grid that we need.
They are. And if that wasn't enough, we're going to compound the problem even further.
Oh no.
You may not be surprised to know that just last year, the American Society of Civil Engineers gave the U.S. energy infrastructure a D+ on their report card. This is the backbone of the world's largest economy, getting a D+ on its infrastructure, stating there is almost a $600 billion investment gap just to modernize what we have.
When one informs that grid, well, they take an inventory of our current active grid, and they see that 70% of our transformers and transmission lines are over 25 years old. 60% of our distribution lines have been there for 40 years or more. So when 60% of your circuit breakers are pushing 30 years, you're not running a modern grid.
And on top of the aging infrastructure, we all know weather-related risks are only increasing. From 2020 to 2024, there were 62 large transmission outage events. 61 of them were weather-related. So we have a grid that was built for a climate that no longer exists, and these temperature extremes are breaking the system.
Yeah, and when we need our grid most is when you're in the heat dome or the polar vortex. Those are the events that then find the weak points in our infrastructure and take down the system that's supposed to help keep us safe. And so this resilience conversation has rolled across the country, right? Florida had the terrible hurricanes of the mid-2000s. California's had the wildfires. Texas had Winter Storm Erie. Now every region is grappling with its own version of climate-driven grid stress.
The challenge is that we have this massively fragmented system without the incentives to actually invest in the infrastructure itself the way we need to. We've got this increasingly aging grid in a very aggressive climate, and it's just not built with the resiliency and the redundancy that we need. And that underinvestment, due to the lack of incentives, due to the fragmentation, is what is keeping this grid so fragile and underdeveloped.
That's right. And I spoke to a startup founder who worked as a lineman for a number of years before starting his company. And he put it this way. He said, the grid isn't just a physical system. It's a system perfectly engineered for the avoiding of blame, right? Where every actor has at least two other people that they can point to whenever anything goes wrong. And so a change maker, maybe inside of a utility or inside of a regulatory body who sticks their head up, just faces downside when things might go sideways and none of the credit or upside of actually pushing something through. There's so much incentive all throughout the system to keep things the way that they are.
And when you think about a system where the incentives are set up for utilities to push blame onto someone else, and the grid keeps getting older and older, and underinvestment continues in an environment where the climate is just getting more aggressive, who's left holding the bag? What's the outcome here? It's the ratepayer. It's all of us.
That's right. And we're at the beginnings of an affordability crisis for electricity in this country. Nearly 1/3 of US households couldn't fully pay their energy bills in at least 1 month of the last year. And affordability is a particularly local story that has now become a very national conversation.
If you look at average residential energy bills in 2025, they were about 30% higher than in 2021. Now, in some areas, this tracks overall with inflation because we've been experiencing that across groceries and gas and housing. But in more than half the country, electricity rate increases are outpacing inflation, and in some cases, quite dramatically.
And it is really a hyper regional story. So it's worth understanding what's going on across various regions. So in California, it hits ratepayers twice. First, they have to pay for all the liability from all the fires that happened. And then second, they need to go pay for all those investments that the utilities want to make to reduce the chance of wildfire going forward, like undergrounding power lines.
And in Hawaii, electricity prices track oil prices because the state remains so heavily dependent on imported oil for electricity.
The Midwest prices are actually going down because they have a lot of wind energy in states like South Dakota and Iowa.
But in the Northeast, it's a huge reliance on natural gas. And so that's driven some of the steepest price increases in all of the country.
The Southeast, we've had all the hurricanes, flooding, and heat driving up rising costs and disaster recovery and the need to continually repair their infrastructure.
And as we know, Texas is deregulated and competitive, which means it can be fairly volatile, sometimes tying closely to natural gas, but also buffered by solar and storage.
And in the Pacific Northwest, hydropower continues to keep us insulated from price spikes. There's been some increases in Oregon, but we're still holding on pretty okay in Washington.
The overarching message here is that there's no single national explanation for rising power bills. The drivers of the affordability crisis are deeply regional, shaped by each area's energy mix, climate risks, infrastructure age, and particular regulatory structure.
The main culprit of cost increases is generally not the cost of fuel or generation. It usually is the increasing cost of transmission and distribution and the upgrades needed to keep that infrastructure running. Transmission and distribution costs are roughly now twice generation costs on the average bill and continue to climb.
And so, what about the question that your mom and my mom keep asking us? What about all these data centers? Well, the answer is it depends. In PJM, which is serving 67 million people across 13 states, there actually have been some real impacts. We've seen capacity prices jump 9-fold in a single year, and data centers are responsible for a majority of that increase.
Let's unpack a little bit more exactly what that means. It means that ratepayers need to pre-fund the build-out of generation in the PJM market to handle more capacity. This has translated so far into over $9 billion in additional costs to fund this market, and this shows up directly to ratepayers as roughly on average $20 per month more on their electricity bill. This is in households from Ohio to Maryland to DC. So, I think your mom is affected by the increasing desire for data centers to build in PJM.
She is living in Maryland.
My mom is like California, not so much.
Now, governors are furious because you've got some obscure grid operator called PJM, which they probably didn't know existed when they got elected, that's effectively determining their voters' utility bills.
And as you can tell, outside of PJM, it's a little bit more complicated. So, a recent Lawrence Berkeley National Lab study found potentially the opposite, that states with higher load growth actually typically were seeing smaller price increases. And in some cases, prices actually fell. This makes a lot of sense, as you can tell by this point in the episode. The more load that can be served from the existing infrastructure spreads grid cost out, and everyone should benefit from decreased prices to help amortize the fixed costs of the infrastructure that we've built.
The villain isn't demand itself, it's concentrated demand in certain places that require massive new infrastructure to serve it.
And I think in this moment of intense uncertainty in forecasting how much we're going to build and where and when, I think there's a lot of questions of, do we have the right mechanisms to coordinate the urgent data center build out with the slow structures of the grid? And it's actually a space where there's been some innovation, right? Should large data center builders be left holding some of the bag if they don't show up with their load eventually? Should we have a different tariff structure, right, to charge differently for those? And so it is a space to watch as over the next few years we work through this into our regulatory system.
And so, whether it is data centers being built in a certain location, or the fluctuation of natural gas prices, or wildfire risk in a certain part of the country, the current path we're on is unsustainable for Americans. That has become abundantly clear. The affordability issue is heterogeneous, but if real rates were to rise 20% nationally, it would push nearly 5 million households into an energy burden. This is a real cost to real families that are already having a hard time making ends meet.
This becomes especially true when more of our load becomes how we heat and cool our homes in an increasingly volatile climate. Air conditioning goes from a comfort to a necessity. And so I think it's really worth looking at this and appreciating what it means if prices keep going up and we're not able to return back to the era of cheap and abundant electricity.
So we've got this crazy demand surge with an aging grid amidst a changing climate and an inability to build anything. All of this is causing affordability issues.
And you must assume that we're using every bit of capacity that we can, right?
You would think so, but the grid runs at roughly 50% capacity. Think about that. It's like if airlines operated like utilities, every plane would be half full. We've built this massive system sized for the worst hour of the worst day of the year. And so when it's not at that peak need, it's sitting underutilized the rest of the time.
There's capacity waste up and down the stack. One analysis put the potential national savings at $150 billion over the next 10 years, just from better utilizing the grid we already have.
And so why haven't we? Well, it's part technical and part regulatory. Remember, the investor-owned utilities earn on that capital invested, meaning they make money by building big things, not operating efficiently. So in 2023, utilities were authorized an average return on equity of 9.5%, while their cost of equity was actually under 7%. That spread of nearly 3 percentage points cost ratepayers approximately $50 billion a year in excess charges. If the return on equity actually equaled their cost, every dollar would go 25% further. So we're actually living in a system that rewards inefficiency.
If a new technology comes along that drives energy efficiency or the utilization of distributed energy resources or improves our grid with grid enhancing technologies, those things that promise to defer or head off new capital investments, those are investments that would threaten the utility's profits.
Right. And these technologies exist. Advanced conductors can double the capacity of existing transmission lines.
We limit lines. We're, of course, worried about what's going to happen to lines on a hot day when they're sagging and transmitting too much power. So we limit lines based on a presumed temperature threshold so they don't overheat and oversag. But on a cool day or a windy day, they can carry much more. If there is a light breeze, wind of just 2 miles per hour, studies show that the capacity of a line can go up by more than 40%. So we could, of course, detect that breeze or temperature and allow more power through those lines. This concept is called dynamic line rating and can increase the capacity of our existing wires.
And then there's the promise of what's called virtual power plants, aggregating rooftop solar, home batteries, smart thermostats, and EV chargers into grid-responsive fleets managed by software. The grid could evolve from a one-way top-down system to a multi-directional distributed network.
And I know we've given utilities a hard time, but it's actually the whole system they're in. So I spoke with someone who works within a utility who is trying to drive some of the adoption of this for their EV program. And they said that they know what they want to do, but the regulator meeting to do this only happens once every 5 years. We're talking about new things like EVs that we need to orchestrate, and we're just not moving quick enough.
And so the vision for what this soft power approach looks like is a high adoption of distributed energy resources that are incredibly flexible and dynamic, that aren't interconnected across multiple geographies to meet our peak loads while increasing reliability and resilience of the grid.
And these ideas are not new. We've had folks excited about many of these concepts for decades, but I think the moment is new. A PUC advisor that we spoke to said that grid utilization is a top buzzword for 2026. After so many years of build, 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 the focus is starting to be how do we make better use of existing infrastructure? And we're starting to see some of this slide into the regulatory conversation. We saw some progress in a Virginia bipartisan vote to make grid utilization a key focus. It was pushed with the help of a new group, the Utilize Coalition. Everyone's starting to realize that it's a resource agnostic, politically pragmatic, fast and cheap approach to increasing the capacity of the grid.
And it gets us to a place of thinking about utilization from a couple different dimensions, which connects the world of the grid to the world of data centers. It's actually an area we found ourselves spending a lot of time in from the venture fund side. So on the one side, we've talked about the grid sized for peak demand for those really hot days and really cold nights. Then you think about the data center. These are also ironically provisioned for their peak potential and also often underutilized, just like the grid. And for a data center, it's underutilized both at the GPU level, where compute power is sitting idle more than half the time, and at the site level, where peak power usage is only used occasionally, and the other times power is available but unused or stranded.
And so when you study it, you realize that a data center and the compute inside of a data center has a tremendous number of knobs or levers that you can control to impact the power draw of the building. You can flex on-site generation, batteries and generators. You can tune cooling systems and pre-cool when the timing is ideal. You can manage server racks, and you can manage down to the jobs that you're doing on an individual machine. We have truly unparalleled control of the power draw inside of data centers, the clock frequency of the GPUs, the exact timing of when and where in your data center fleet you put a training or inference job. All of this means that there's an insane amount of capacity sitting in the system, and that no data center is actually running at that full nameplate capacity, and few GPUs are being fully utilized.
And the potential is tremendous if you're able to pull this off. Last year, we learned from a Duke paper that if data centers accept just a quarter of a percentage point of curtailment to their entire load, which is about a day per year of reduced consumption during peak hours, the US could add over 75 gigawatts of new data center load without building a single new power plant. You push that to 4 days of curtailment, and that number jumps up to 126 gigs.
There's a big mismatch in timelines that feed into all of this as well. Remember, data centers want to hook up now, and it's going to take many years or decades before we get the power generation to grow. So utilization is key, but we need big updates to unlock this. The capacity is there theoretically, but we need market signals, regulatory structures, and utility incentives to be set up to actually enable the market to utilize the capacity we have. And not only that, but if we go back to the growth of our grid and the magic flywheel that Insul had pioneered, that essentially adding more load across more customers drove costs down, that brought on more load and more customers and drove costs down. This is one of those moments, and better utilization of the grid is one of the most effective things we can do. So we've arrived at the end of our story through to present day, but I think we should pause for a moment and get our hands around the current scale. Let's imagine that we hop in a hot air balloon, we fly up high enough to see the full US power grid. We'd observe all the power that's flowing in and the diversity of generation sources, from the spinning mass of turbines to the panels capturing power from the sun, storing it into batteries, and moving it around the country. This grid is powering all the forms of load, from the light bulbs in our house to the data centers now being plugged in.
And if we look at the grid from that altitude, we would see that the US doesn't have a utility. It has nearly 3,000 of them with a few different flavors.
That's right, 170 of them are these private investor owned utilities. 2,000 are these publicly owned muni utilities, and 800 are the co ops from the Rural Electrification Act era.
And together, they manage 700,000 circuit miles of transmission lines and 5 million miles of local distribution lines going right into our homes.
And that's why this whole system is called the largest interconnected machine on planet Earth. It's because those millions and millions of miles connect to over 7,000 power plants that then pulse at 60 hertz.
Man. And all of this hangs together in the Eastern Interconnect, the Western Interconnect, and Texas, connected by a handful of high voltage DC lines and substations, keeping everything working in harmony.
And what exactly is that grid powering? Well, our homes are nearly 40% of the load. Commercial offices are 36%, and industrial loads are another 26%. And across these, the largest use is heating and cooling our collective spaces.
And how is it doing all of that? Well, currently, natural gas is by far the largest generation source at about 43%. But renewable energy is growing to almost a quarter, while nuclear sits stably at around 17% of generation.
Our old friend King Coal, down from his high of 50% to now 15% of remaining capacity.
And within this, the thing that we're excited about is we've consistently seen year after year over 90% of new capacity added to the grid is in the form of renewable energy.
And so, how powerful is this system? How hard is it pumping? Well, the total installed capacity is 1,300 gigawatts, but the peak we've ever drawn at a particular moment is just over 750 gigawatts.
And in addition to power, what else is the grid producing? Powering the grid creates about a quarter of our total greenhouse gas emissions. But the good news is these emissions have fallen over 40% since 2005, largely driven by that shift down from King Coal.
And it's an important point that the US grid emissions have fallen faster than almost any other sector of the economy. And that particularly matters because the grid itself is going to enable the decarbonization of almost all the other sectors.
And so where does this all leave us? Well, I think it leaves us fairly awestruck at the history and complexity and size of the grid. So let's unpack some of that awe and appreciation that we're feeling.
For new listeners, what we like to do after the full story is look back and think about the big takeaways for us. What and I are our big themes and reflections.
Oh man, my head's spinning at 60 hertz. One level of appreciation is just sitting in this feeling of awe for this almost magical machine we've built.
I think to realize the true interconnectedness from my house to yours, my lights above my head and the lights in your room are receiving power that is synchronized and that's tied to the generators at the hydro dams and the coal plants and the nuclear plants. It's a true awe-inspiring physical thing.
The image that is now implanted in my head is a school bus spinning at 3,600 revolutions a minute. And this is all in sync with all the different school buses spinning up and down the West Coast.
I actually can't plug in my car or turn on a light switch without thinking about the fact that that creates this physical drag that adds a little braking to all of those school buses at the same time.
I think another level of this appreciation is largely based on this historical perspective that you and I have now gained over the months of nighttime research. And one thing I'm struck by is something this complex and this large and this important was built less by design and more by historical accident of both circumstances and isolated decisions that then had reverberations across decades.
We've thrown out these numbers, 3,000 utilities, but each of those is their own place and fiefdom of rules and rate cases and regulations and customer service calls and linemen doing the work and all of them building out piece by piece this machine.
You mentioned the linemen, like really amazing people working inside these utilities who maybe could have gone on to get more lucrative jobs, but they feel passionately about reliability and delivering this services. It's remarkable when you actually interact and talk to folks that work in a utility. They take their job, rightfully so, very seriously.
It's a form of frontline service. And it is still, I think, one of the most dangerous jobs in America is being a lineman because you can be electrocuted, you're at heights. Back to the zoom out on the historical accidents, you think about the history of the grid is the history of all these different eras leading to push-pull moments of economics and regulation and what the country needs, wartime, and all of these pieces.
How the puzzle fits together from the AC/DC wars and how AC won out to Samuel Insull coming in and through his own genius of a mind, understanding that the business of electricity functions more effectively when you have larger generation creating more kilowatt hours spread across more people. And that created a business model.
For some reason, in a way, I think he's been a little shortchanged given how many businesses have since adopted this, especially businesses like Amazon and cloud computing and now neo cloud computing. But I feel like we should call it Insull's Law at this point, which is
Trademark.
step change is named Samuel Insull's Law. I'm not proud of him for his holding company financial shenanigans, but this key insight that driving a high number of people to use your thing more and more by making it cheaper creates a flywheel that drives you to make it bigger and continue to make it cheaper and drives utilization of expensive infrastructure is a foundational business model that continues to drive, I think, the economics of every element of the power sector, the computing sector, and so many others.
Yeah. Increase utilization of your large asset, amortize the costs across as many people as possible, while bringing down the price to further incentivize people to use more of it and spread the cost out. It's genius. And then you go from him to then, the decision, because we're post-depression, of breaking up the holding company and creating the regulated monopolies in these state-sized geographies, right? Puka in the 1930s, has fundamentally shaped the course of American history.
And a lot of the complexity that we just covered of why things are so hard to build now and the moments that we were able to break through that when the country really needed it. There's just a bunch of weird little things and echoes in history, right? We didn't get to go too deep into this, but San Francisco had a running DC grid until something like 2012 because they had some elevators downtown that still needed DC. Japan has one 50 hertz grid and one 60 hertz grid because of historical accidents. So you just have some fascinating tiebacks to the history of regionalized subgrids that over time became more and more interconnected.
You can fast forward through the wars happened, and therefore we have things like TVA and BPA, and therefore we have transmission line buildouts, and therefore we have power pools. And then the post-war economy, the post-World War II economy in America was one of the most powerful things man has ever created. This engine of capacity, largely built on power generation capacity, that then fueled an economic miracle of a generation.
My mental image of that era is Reagan telling people they need an all-electric home. He was literally it was like rewiring America of that era, not for obviously any climate ambition, but to drive Insull's business model forward. Like, we needed more utilization, so we're going to tell people we should electrify everything in their house, and we're going to give them a gold medallion if they do. What an amazing boom time for electricity.
Yeah, you love the gold medallion.
I love the medallion. I want a gold medallion in my house.
And then you go forward and continue on through into the oil shock and the 70s, where everything turns upside down from a pricing and access of fuel perspective. And then you have this confluence of the conservation movement coming in right at the same time that leads to then, of course, the image of Jimmy Carter with the cardigan sweater, right?
Yeah, and that one, I can't help but just think about the moment we're in today with an oil shock. In a lot of ways, it echoes back to that, and it does for various grids around the world. But actually for the US grid, it doesn't particularly, because we have so much domestic fuel generation now versus the import dynamic we had in the 70s. And largely most, our grid is very much off of oil. But a lot of our energy is still oil. A lot of our transportation is still oil. It's not just about the grid in that context. It's more about the relationship between broadly energy and the economy. It does not mean that a massive oil shock couldn't wreak massive havoc on our economy.
Totally. That's a great point. Yeah. And then we roll through into the 90s and just the complete disaster of an attempt to deregulate, re-regulate, actually just restructure, which was particularly acute in my state of California. But man, we bungled it.
Yeah, I remember being a kid and watching Gray Davis get recalled. I didn't quite understand. I knew there were energy crisis. I'd heard a little bit about it, but I was living in California at the time, and I just remember this vitriol about how the whole thing was being handled, and I think it scarred a lot of people around just any changes to the system and really entrench status quo.
Yeah. And I mean, rolling blackouts for months on end. And
Not out of technical necessity is the point, like out of market failure.
we roll into a period of 9/11 and the Iraq War. We find shale gas, the financial crisis. Things start to change again.
Yeah, I mean, we hit on this in the coal story too, but like this just reminds me about the complex feelings I have towards the shale gas revolution. And from a climate desire, coal is just so bad to be burning at this point if we don't need to as a species. And anything we can do to stop burning coal is so good from a progress perspective. And yet, obviously, we need to get fully off of all fossil fuels. Seeing it again from the grid perspective and getting a deep appreciation for, like, if we had not had the shale gas revolution, it's very possible that we'd be in a quite a different emission state as an electricity grid in this country today. And that is just a complicated feeling to sit with.
Yeah. I mean, we needed the market to solve this problem because we didn't have the wherewithal from a policy perspective to be able to do so. And we priced out coal. That's the reason it fell. There was also a movement around legislation and climate awareness, but it was no means as powerful as price.
And in 2007 through 2015, like, solar was not where it is now.
Yeah.
Right? So we're in a very different moment now with solar and where we're entering with storage, but it really made a difference in the last 15 years that gas was able to knock out coal.
It's odd when you live through a revolution that happens slowly, you don't have as much appreciation for it. And so through our working life, solar has gone from a niche product that was completely an alternative idea that was attempting to be commercialized to, over the period of less than 2 decades, the cheapest form of energy. It really is amazing when you're able to step back and appreciate it.
Almost called a step change. We haven't used the word very much. And same with EVs and batteries, right? Like, it was not that long ago that buying an EV, it was competing with a Mercedes or a Porsche or a BMW in cost and luxury. And now, I was just in Mexico City and they're advertising the $10,000 BYD EV. Watching solar and batteries go through that, really, not just in our lifetime, but in the last 15 years, I think is a miraculous setup for what's about to happen.
Yeah. I mean, another thing we're living through is the changing climate and its impact and an ever-aging grid. And you combine these two forces of really old, complex infrastructure with really powerful changing climate that the infrastructure was not built to handle or withstand. I gain a greater appreciation for resilience and adaptation as a theme and a reality of our life.
It's just so central on both sides of this, right? It is the central ability that we have to electrify a bunch of things and therefore decarbonize them. But then even more acutely and more pressingly, it combined with the drought conditions is starting fires. It combined with the weather is causing power outages, causing people's medicine to spoil in the fridge or the hospital to kick on the backup power. And so our general analogy for the grid and the body, I think, is the circulatory system because it's bringing energy to everything.
Yeah.
But in this way, as infrastructure, it's a little bit like the skin. It is the surface that's hitting the realities of climate change first from an infrastructure perspective. It's the first line of defense that we're going to consistently experience. And the American grid was just really not designed for the moment we're in now.
Yeah. Every day as energy investors, we're reading articles about demand and, of course, data centers. And we know it intellectually, but to put it in context historically of decades of flat growth and then this just massive spike in a very short order, combined with the realities of the grid and utility incentive models and everything else, I think, to me, it adds this new layer of appreciation for the gravity of the moment.
Yeah, absolutely. There's so many things to say about the collision of growth of demand, the affordability crisis with aging grid, with data centers. But I actually think part of my takeaway looking back through history is we're all befuddled because we actually haven't lived through that before. But if you talk to a bunch of people that lived through the wars and lived through the buildup of TVA and BPA, this country has lived through massive electrification growth before. Remember, 1920, entering it, almost no one had electricity. By the end of that decade, almost everyone had electricity. Like, talk about demand growth.
Yeah.
That's just not like one sector, but that's like connecting everyone's homes and inventing the outlet. So I'm left with a little bit of like, we've just ossified our comfort with growth in something like this, and we've ossified our ability to see infrastructure as something that we can radically build and force our institutions to evolve to meet the moment. But that's just because no one running the institutions, not that we were either, were there when we needed aluminum to build the bombers to win the war, or needed to power Oak Ridge to design the bomb. We stood up New York City level demand in months when we needed it by forcing the build out of dams, by connecting power pools together. So I'm left actually hugely optimistic that if we choose to, we could not just meet the moment, but excel through it and look back and say, wow, that was this moment of massive upgrade of the grid, like maybe we haven't seen since the 30s.
And that's why we're investors in the future, because we believe we have some agency. The hard part for the human mind is you look back at TVA or you look back at rural electrification and you see the awesomeness of what we did, but that also took 3, 4, 5, 6, 7 decade, right? Like it took time, and we're now living in that moment every day and experiencing it. And so the time dilation is difficult to handle. But to your point, if you step back and look at the mid 2020s from the 2030s and say, oh, how we overcame this collision, that is the opportunity. I think for me, we're in a moment where the stakes are very high. And you think about what's holding us back. So to your point on optimism, we have the choice, right? Because this isn't a capital issue. We have capital. This isn't a technology issue. We've created a lot of the technologies that we are going to need for the next 5, 10 plus years. It's an institutional issue. It's a man-made problem of our doing, of our creation and our choice. And to be able to see that and feel that is both, I think, frustrating, but also creates optimism.
What is underlying that institutional calcification and resistance? And I think back, it's not like everyone was on board with TVA or BPA. Like, it's not like there
Right.
wasn't a lot of resistance. There was. These were hard fought battles. There were people that sued to block the build out of these things.
Multiple times.
And so what did you have? Well, first of all, you had leadership that pushed through. At the end of the day, it all comes back, I think, to incentives and where incentives weave through in the system and how powerful are those incentives and the people who are incentivized by them.
100%. We're in this moment of needing to reframe our relationship to the grid from this passive infrastructure that has done its job more or less for 100 years to something of national security importance, something of geopolitical relevance, something that is going to define the transition of America from a petrostate to an electrostate. The gravity of if we don't make that leap fast enough, or we don't make that evolution fast enough, how far behind we will be to obviously China, but even others, right? When they're building 9 times the generation capacity we are every year.
If energy equals compute and compute equals economics, like what does that mean?
Yeah.
Right? What do you think when you look back at kind of all the players and all the incentives and all the structure? What do you think are the incentives that are most salient?
Amory Lovins decades ago coined the hard path and soft path of the way to build out our future electrification. And I think we've arrived at the conclusion that it's a both and. It's not an either or. We need to utilize the grid that we have to more than a 50% load factor. We need to build out distributed energy and microgrids to create the resilience and the redundancy and the flexibility that the grid needs. I want to envision a future where we can build, and the incentives around not being able to build multi-state, ultra high voltage transmission lines will keep me up at night. So what do you need to do about it? This is a point where I don't see another option except federal overreach. Centralized planning coming down from the top, paying for it, cutting through the incentives, ignoring the lobbying, and doing something that is not in any individual state's interest, but is in the national interest.
I think that's right. I'm trying to think about the characters on the board right now.
Mm-hmm.
You have all these little utility fiefdoms. Some of them are city level, like Seattle City Light. Some of them are the investor-owned utilities. They have their hyper-regional incentives, like their bureaucratic incentives of staying and growing in power, right? You have the states trying to ostensibly look out for the people in its state, but has these powers to block anything that passes through but doesn't help. You have the fossil fuel industry, the coal industry, the solar and wind industry that has their incentives to try and privilege their form of generation. You have the tech companies trying to get their data centers plugged in. And you have the ratepayer trying to afford the electricity that they have and ideally have more abundance. Ideally, get to a future where it's cheaper to heat and cool your home and cook your food with electricity than it is with any other option, as it should be if you go back to the basic physics and economics. If you zoom in at that level, thinking which of these players on the board either should have a change in incentives or like shouldn't be on the board in quite the same way anymore. Like when it comes to transmission, if we're going to really be a country that builds, we need to probably remove a lot of the state's abilities to block transmission. Then you can get to what a China has, where you can take advantage of resources across large distances. But then also this whole investor-owned utility return on equity incentive model also leads to some of the wrong ways to invest in transmission and distribution. So I think we have to rethink the fundamental structures of this stuff.
The return on equity and guaranteed rate of return that is measurably larger than the cost of capital was, I think for both of us, such an eye-opening and alarming understanding of just how much, not only that that affects ratepayers and holds back investment in certain necessary grid-enhancing technologies, but that it also forces the hand of the good people working in those utilities, right? The
That's right.
utilities are not the enemy here.
No.
And I think oftentimes we can make them out to be because they're a big actor and there's problems, and so you look at the big actor. But actually, right now they have a fiduciary responsibility, and their leadership will ostensibly get fired by their board of directors if they don't seek the most profit-maximizing solution. It just so happens that the profit-maximizing solution is not in our interest in this moment. And so if we can realign their incentives, they can go and do their job even better.
Most people working at most utilities want to do and can figure out the right thing to do, but you talk to them and they're in a structure that incentivizes very clear certain behavior and disincentivizes others, and it just drives everything. Doing this work has made us, I think, so much crisper about then what does it mean if you're trying to sell into a utility? I think this moment that we're in of collision then further makes me optimistic because it has a moment to really shake up the status quo. It has that kind of 1930s echo moment of, okay, we're going to need to be able to build our way out of this and therefore can question a bunch of the ways that it's been ossified.
Totally.
So let's say we go and unstick some of these incentives. What do we think the next 5 to 10 to 20 years are going to look like, potentially, in our ability to grow out of this?
Where we have to go is more and more towards this selectro state that we've mentioned. And the things that are breaking down today as a result of this new, very large demand growth is actually just marginal increases in capacity and load. This is the beginning innings of a multi-decade growth story. And again, it's one of the things that we talk about the energy transition. We invest in the $1 trillion energy transition, but I actually think trillion is selling it a little short. We are talking about 20% of total energy use in this country that comes from the grid. And in order to keep up across defense and pharma and biotech and compute and AI, all these major industries, we're going to need to grow the grid's share, the electrification's share of our energy use to 40 to 50%. So we need to build 2 or 3 more of our existing grids over the next 20-ish years. And that, to me, just suggests that this is a beginning of a generational moment. And it's going to be multi-trillion dollars.
Yeah, and I think that combined with the real beginning on-ramps of storage as a technology defines the structure. Because think about it, we experience right now a form of this in our life with our phone or our laptop or our car, right? These things that we can plug in, charge, and they're sometimes grid connected, sometimes not. And so this is not a new concept, but when our house starts to feel more like our phone, and then our neighborhoods feels more like that, or the data center starts to feel more like that at kind of various levels of resilience, energy arbitrage, syncing with cheap renewable sources, combined with massive new transmission and generation capacity, I think I can see what that looks like. And I can see how you can triple our grid, both using a lot of thoughtful central planning and execution alongside the magic that storage is about to unlock for all of us.
Totally. I'm glad you bring up storage because the more we learn about the physics of the grid, the more we realize that everything that's been created was created on the basic principle that you have to consume what you produced in that exact moment. And we are finally reaching a moment where that fundamental law of the grid has a companion here in the battery. And it almost feels like, to do that justice, we might need another episode, but TBD.
Maybe we'll give ourselves a little break. It's funny. I was at dinner last night with my daughter, and she turns to me and says, "Can you guess what I'm thinking about?" It took me a couple guesses, and I wasn't getting it. And finally, she told me. And then I said, "Can you guess what I'm thinking about?" And she said, "Yeah, the grid." How do you know? Well, here I think ends our story. Goodbye, grid.
It was an electric one. Thank you for powering through.
Hope it sparks some new thoughts and conversations.
We could go on all day.
Let's unplug.
And one big ask of you all now. We know your attention is valuable, and we're super grateful that you spent time listening and learning with us. If you found this episode helpful in better understanding the grid, we would love for you to text it to a few folks, drop it in your work Slack, or share it on LinkedIn or Twitter, and feel free to tag us. As you can tell, we love chatting about this stuff.
Yeah, not just on the mic. We love thinking about this all day long. As you may know, this whole podcast project is an endeavor of our fund, Step Change Ventures, where we've built a portfolio that touches energy, infrastructure, resilience, and more.
And of course, the grid is a huge topic for us. Over a third of our portfolio in some way involves upgrading the grid.
We're seeing some interesting buckets emerge. As we reinvent how the home is powered and controlled, we have companies like Balto, Wattbot, and Bayou that are central to that.
And then as we think about the layers of the grid, we've got this infrastructure that's being built by utilities who have to make investment decisions or enable the AI transformation. And companies like AZX and Rhizome are doing just that.
We've talked about how much capital investment needs to happen to improve the grid and particularly deploy renewables at the pace they should be from an economic standpoint. And so we have Distill, Cape Zero, and Ezra all helping in some part of that tool chain. And this whole area of the collision of data centers and the grid and improved utilization, we have companies like Hammerhead, Lucend, and Lumerian all operating from the GPU level all the way to the building level. And how do we get more out of the power capacity we have? So much fun stuff to be done across this whole stack.
And so if you're a founder working at the intersection of grid, data centers, or any of the tooling to improve this world, we would love to chat.
And over the next year, we'll be growing our firm significantly. So don't hesitate to reach out, shoot us a note, and we'd be happy to share more. All right, with that, we have some big thank yous. First, to Crusoe for being the first Step Change presenting sponsor. They're an incredible company building data centers and power systems end to end. Head to crusoe.ai/stepchange to see how they can help you build faster.
Thank you, Crusoe. Next, there are some key backbone resources that have helped really frame our story. So thank you to Jill Jones for writing Empires of Light and Gretchen Bakke for The Grid. We did read another 8 or 9 books, but these two really stood out.
And thank you to Jane Woodward and Amory Lovins and their teams at Stanford for building out a phenomenal set of resources on the entire energy landscape and on radical energy efficiency, all linked in the show notes.
We also listened to over 50 podcasts, particularly episodes from Open Circuit and Volts, that have been great to help us ramp up on the full set of regulatory issues that are currently facing transmission growth.
We really wanted to thank the following people who were gracious enough to take time on calls and over coffee.
Thank you to Jigar Shah, who has worked on many different sides of this ecosystem and whose recent podcasts, Open Circuit and Energy Empire, have been great resources for us.
And Liang Min from Stanford and Jesse Jenkins from Princeton, who have done some of the deepest modeling about the future of the grid.
We also talked to great writers, including Brian Potter of Construction Physics, David Roberts of Volts, Peter Kelly Detweiler, who authored The Energy Switch, and Arthur Downing, who's about to publish Power and the People on this very topic.
And Michael Thomas and Ramez Nam, who walked us through the big data stories that touch the grid.
And we also got to sit down with an incredible set of folks that have been in and around this industry for the past couple decades, including Julia Ham, Rob Gramlich, Cameron Brooks, Mark Ellis, and Robin Meslowski.
This includes Michael Skelly, Josh Gould, Connor Doyle, Alex Collins, Matt Estes, Aaron Hardick, Tim Barat, and Nat Bullard and Sam Steyer at Halcyon.
And a big thank you to Matan Nice, John Zemmel, and Skander Gorham. And up on stepchange.show, we've embedded Matan's interactive learning tool that he actually built alongside our research work.
It's very cool. And on crafting this podcast, Jenna Herzog helped us build out this interview list, and Ben Gilbert of Acquired, who has continued to mentor us through this absolutely insane project. And of course, a huge shout out to our editor, Nick Patry, who makes this 4 to 5 hours great instead of 10 plus hours of us babbling.
And finally, and most importantly, a huge shout out to our wives, Anna and Sheba, and our kids, who've given us a free pass on too many nights and weekends to make this all happen.
All right, well, until next time, thank you.
You can can make your family's life much brighter. You will find your work much lighter. It's as easy as can be to live better electrically. You can have more time for fun and pleasure. Family moments you will treasure. It's an opportunity to live better electrically.
Modern folks have learned to save their time and energy too.
You don't have to work and slave. Let electricity do it for you. You can have your cake and you can eat it. Make life sweet, it's hard to beat it. What a thrill to be so free when you live better electrically.